and good afternoon, everybody. I welcome you all to the afternoon session of Curry Lift Days, Day 2. Today we have an invited speaker to begin with, and it's my great pleasure to have Shivansh Pandey as the chair for this session. Shivansh completed his graduation from Allahabad University and master's from Banaras Hindu University. Currently, he's a research scholar in the School of Mathematical Sciences, NISER Bhubaneswar. He's working under Professor Brundaban Sahu. Shivansh.
Thank you, Kiran here. Thanks for the introduction. So, good afternoon, everyone, and welcome to today's lecture. So, it is my great pleasure to have Dr. Brundaban Sahu with us. So, he did his PhD completed his PhD in 2008 from Harish Chandra Research Institute under the supervision of Professor B. Ramakrishna. After that, he went to University of Dublin for his postdoc. In 2010, he joined NISER Bhubaneswar as a faculty member. Currently, he is an associate professor and chairperson at School of Mathematical Science. His research areas include number theory, modular form, Jacobi forms, and representation of integers as in terms of certain quadratic forms. So today he will speak on sum of squares. Over to you, Sausa.
Yeah, just a minute. Yeah, the screen is visible, Shivansh?
Yeah,
yes,
it is visible. Just make it full screen.
Yeah.
Yeah, now it is fine.
Okay, we'll start.
Yeah, you can start.
Oh, okay, thank you very much, Shivansh, for this kind introductions. I'm very grateful to the Curry Lift teams for organizing these nice events. I'm thankful to all the members of the organizing committee. Also, I'm in particular thankful to our postdoc Kiran Kumar Behra for his invitations and give a talk in this forum. So today I'm going to speak on sum of square, which is something like expository talks. So as in the first half, basically I'll go some of the elementary result known on the sum of squares. Basically I'll discuss 2 square, sum of 2 square, sum of 3 square, 4 squares, and try to generalize for any even number of squares. Then at the second half, as yesterday we saw the Professor Balaji's lecture on complex analysis with his viewpoint to other areas of mathematics. So today we'll kind of relate complex analysis again with this number theory, namely this topic sum of squares. That's my aim. So if you have any question in the middle, please don't hesitate to ask me any questions. Yes. Yeah. So let me start with this. Yeah. So by squares we mean the numbers 0, which is 0 square, 1, which is 1 square, again minus 1 square. 4, 2 square, as well as minus 2 square, square of minus 2, and this number 1, 4, 9, 16, 25, 36, 49, they are all the squares numbers. That's what we mean by squares. So basically, there are 2 classical questions started 3rd century by Diophantus, namely, which positive integers can be written as sum of k square. K may be 1, 2, 3, 4, or k may be any number of squares. So basically, we can ask the questions which positive numbers can be written as sum of k squares, and which positive integers cannot be written as sum of k squares. So we are like to find it out. This is basically the question, the first question. And second question, if n can be written as sum of k squares, then determine the total number of ways one can write n as sum of k squares. So we're basically interested on these 2 questions in the first part. Just to be for some basic examples, namely there's 1 equal to 1 square plus 0 square, 2 equal to 1 square plus 1 square, 4 equal to 2 square plus 0 square, 5 is something like 2 square plus 1 square. So this number 1, 2, 4, 5 can be written as sum of 2 squares. But however, you can see that 3, 6, 7, 11, 12, you cannot write as sum of 2 squares. And when you count, this is the other note for the first questions. For the second part, when we are counting the number of representations, we are taking care of all order and summation, order of summations, and the sign of a particular terms regarding as distinct. So, for example, 25, there's a 3 square plus 4 square. We can write this as 4 square plus 3 square. Similarly, minus 3 square plus 4 square. And basically, we are counting as all distinct number of representations. So basically, 25, we are getting something like 8 representation in this way. Although you are taking the care of plus minus and this the order of it appears. And let's.
Sir, I think Gaurav has a question.
Yes. Please go
Gaurav,
ahead.
you can unmute yourself and ask.
Yes, sir. Sir, I want to ask why they are interested in writing any number as a sum of squares. What is behind? Why we need it? Basically?
Yeah. Okay, that's a good question. We'll see after some time you will get your answer. Why you interested? This gives very beautiful mathematics.
Okay. Thank you.
So let's start with the elementary things, but after some time we'll see the many methods, beautiful methods will come into the picture. Okay. So we'll see that. Yeah. But it has nice application in maybe in lattice theory or some of this theory either to physics, cryptography. A lot of applications are there. All right. So let's start with the basic things. All right. Okay. We'll discuss.
Okay, sir.
Yeah. So let's come to the sum of two squares. So basically, we're asking that find all positive integer n such that n equal to x square plus y square. It has solution in integer. We are looking for solution in the set of integers. And the second question, part of this for the two square, let's define this R2 of n. Namely, this is the cardinality of the set x comma y, x and y both integers, so that x square plus y square equal to n. So given n, we are looking for something like R2n. What is the cardinality of this set? And we have very beautiful identity due to Diophantus. Namely, the identity is very basic, something like one can see easily. A square plus b square times c square plus d square is equal to ac plus bd square plus ad minus bc square. We can change the sign on the right hand side, one negative, one positive. So basically, this identity one can see easily. And this has nice consequence and it has nice mathematical interpretations. And what is the first one? We say that if two integers can be written as sum of squares, then you can write the product also as a sum of two squares. Yes. So if m is a square plus b square, n equals c square plus d square, then you take the product mn, that also a product of a sum of two squares. All right. Also, this identity gives explicit method for taking two numbers which are sum of two squares and write that product again as sum of two squares. All right. So this is something called composition law. All right. So this kind of identity. So basically, we have two numbers on the same forms. We are taking their product. Again, it looks on the same form. That's what basically say this identity. And there are various mathematicians work in this kind of square from Girard, Forma for this sum of two squares. Let me just answer these questions. Which numbers can be written as sum of two squares? And this is theorem due to Euler, but there are several proofs of these theorems. There are many people who work in this area in these theorems. So the theorem says that the equations n, given n positive number, and you can write as sum of two square. If and only if all the prime factors, all the prime divisors q of n, with q congruent to 3 modulo 4 occurs in n to an even power. So what basically means is that you write n as the product of write n as the product of this prime factorization, namely the canonical factorizations. And you look the power of 2, that's called alpha. You look the powers of prime, which are 1 modulo 4. Suppose those prime powers occur as something like beta 1, beta 2, beta k. And you write the prime powers q gamma, where q is 3 modulo 4. And what we are thinking that this number n can be written as sum of 2 square if all the exponents gamma, the gamma occurs as the exponent of the primes of the form q is 3 modulo 4. If those gammas are all even, then you can write this n as sum of 2 squares. And this is statement in both conditions. So you have exactly those numbers which you can write as sum of 2 squares. Okay, and this is part of the elementary number theory. So what we prove that an odd prime p is sum of 2 squares if and only if the p is congruent to 1 modulo 4. Namely, if we divide by 4, p by 4, the remainder is 1. And the second lemma, if q is a prime factor of a square plus b square, and q is 3 modulo 4, then q divides A as well as B. So what we basically say that if Q divides A, Q divides B, then Q square divides A square plus B square. So namely, if Q is a prime factor of A square plus B square and Q is 3 modulo 4, then Q square must divide this number A square plus B square. So they are the two lemmas that we use to prove these theorems. And the computations for R2N, there are various proof of this, how many ways we can write this R2N, how many ways you can write this N as sum of 2 square, that is proved by Gauss using the theory of quadratic forms, again by Jacobi using the theory of elliptic functions. There are several proofs in this direction of R2N. So let me express this R2N. They are also part of this very classical things. So given N, let N denote the number of positive divisors of N. Write N as earlier, N equal to 2 to the power alpha, N1 times N2, where N1 is the product of all prime powers, and the primes are P is 1 modulo 4, and N2 we keep it out, the second kind of primes, namely 3 modulo 4, and write them in terms of gamma. Then we have seen earlier that R2N equal to 0 if any of the exponents gammas are odd in N2. Otherwise, if all the exponents are even, then R2N is nothing but 4 times the number of divisors of N1. dN1 means number of divisors of N1. So he exactly knows what is the number of the way you can express N as sum of 2 square. This just depend on this N1. Yeah. I think I'm making a mistake here. This N1 should be N2. Sorry, that's a mistake on that. This R2N is 4 times D of N2. Yeah, all right. So there's a typo here. So, for example, this R2 for the number 1170. So this is 2 times 3 square into 5 times 13. So this basically depend on R2 times 5 or 5 times 30, that's 65. So you don't know depend on 2 times 3 squares. So basically this is 4 times D of 65, and 65 has 4 divisors, namely 1, 5, 13, and 65. So there are 16 many ways you can write 1170 in terms of sum of 2 squares. All right, and I'm writing all the 16 representations coming from here. All right. So this is the story about sum of 2 squares. Let's move forward. So let me go to the sum of 3 squares. So as you see that the 7 is not a sum of 3 squares, because the squares are 0, 1, 4, less than 7, and 7 you have to write a sum of 3 squares. You have to write express in terms of 0, 1, and 4, but you see that 7 you cannot write sum of 3 squares. So there's a first number which is not sum of 3 square is 7. But you see the number 3. Okay. One more observation we are making here, that the composition rule, we see that for sum of 2 squares, namely the identity A square plus B square times C square plus D square as a sum of other two squares, that is not going to true for this sum of 3 square in the case of sum of 3 square. For example, 3 you can write as sum of 3 squares, 5 you can write sum of 3 square this way. There 3 and 5 are written as sum of 3 square. However, the product 15 in order sum of 3 squares. You can see that because below 15 the squares are 0, 1, 4, 9. Okay, using those 3 you cannot write sum of 3 numbers to get it 15. Okay, so the composition rule is not going to be true in this case of sum of 3 squares. So also you can see if you look the squares modulo 8. Okay, the squares are 0, 1, and 4 modulo 8. So you can see if you take sum of 3 squares, 3 different squares, that we have to have some kind of number, namely those numbers which are something like 7 modulo 8. We cannot get that as sum of 3 squares. So there is a theorem of Gauss, namely the differential equations x square plus y square plus z square equal to n as solutions, or n can be written as sum of 3 squares if and only if n is not of the form 4 to the power k into 8m plus 7. So basically we have to look this 7 class and you have to leave out those things. Other numbers you can write always sum of 3 squares. And one part is easy to prove, but the other part is not easy in this case. And one is the theory of quadratic forms. So let me just, because the difficulty here is, as I told you, the composition rules or the identity, Dafonta's type of identity is not true for sum of 3 squares. So basically how you prove that, basically something, if we have the identity, then you can just attack for the case of primes. But here this is not the case, so this case becomes more difficult. All right, and there is a formula. This formula for R3n, as you see that number of way you write n as sum of 3 squares. For example, you can write 1 as 6 different ways, because 1 is plus minus 1 square. Other 2 terms you can take 0, 0, but you can put this plus minus 1 in any of the 3 positions. So number is given 6. R31 is 6. Similarly, R32 equal to 6. And if you are looking for a formula for number of representation for the small R3n, the formula is not as that easy like sum of 2 square or 4 squares. And basically, one needs the theory of quadratic forms. A formula given by Gauss looks like, okay, capital R3n is the number of primitive solution. Primitive solution means x, y, and z are going to be primitive tuples, namely GCD is equal to 1 actually. So if you look R3n, the number of primitive solutions for these equations, this looks like something like 12 times Hn and delta n for n congruent to 1, 2, 5, 6 modulo 8. And for the case of n is 3 modulo, it should be there is another typo. This is 3 modulo 4. Yes, 3 modulo 8, yeah, because 7 you are taking out, yeah, that's fine. So this is 24 times Hn delta n. Here this Hn is the number of classes of primitive binary quadratic forms with discriminant d equal to minus n for n is congruent to 3 modulo 4, 3 modulo 8, and d equal to minus 4n for the other class of integers. Okay, so basically one need this. There is on the theory of binary quadratic forms, one can have equivalence relations on the quadratic forms. Basically, we by change of variables by unimodular matrix, we can change the variable and we can define this something called equivalence of quadratic forms. Where basically we are looking this number of distinct elements in the different equivalence classes from that equivalence relations, and that basically gives this class numbers. And for delta n is defined like n equal to 1, this is half. For n equal to 3, this is 1 by 3, and otherwise this is equal to 1. So these are they are the solution for the primitive solutions. But if you are looking for the usual R3n, number of solution n can be written as sum of 3 squares. You can apply this R3 capital R3 formula to get the small r3 because of these equations in terms of the divisor squares n by divisor squares. So this what I want to hear that the story for even 2, 4, 6, 8 are different, and the story for odd number of squares are completely different, and the odd number of squares dealing with this is quite different and difficult from the even number of squares. All right, so now move to sum of 4 squares. So we have this classical theorem, namely the theorem due to Lagrange, that all natural numbers are sum of 4 squares. Okay, so we have this basically given any n, positive integer n, you can write this, you can solve this equation x squared, y squared, s squared plus y squared plus z squared plus w squared in the set of integers. For example, 7 was the problem for the sum of 3 squares, but you can see that 7 you can write as sum of this 2 square plus 1 square plus 1 square plus 1 square. Okay, and the interesting thing is that the similar kind of rule as happens for the sum of 2 square, that is true for again a sum of 4 squares, and this identity due to Euler. Namely, if this the first integer is sum of 4 square, second is a sum of 4 square, then the product you can add a sum of again 4 square. Where this z1, z2, z3, z4 we can express in terms of x1, xi's and y like this. Okay, and because of this identity, it is enough to consider that all primes are sum of 4 square. Then you can write all positive numbers are sum of 4 squares. And already you see that p congruent to 1 modulo 4, it is sum of 2 squares. So you can put the extra 2 zeros and you can say sum of 4 squares. So only you have to deal with this sum of for the prime q is 3 modulo 4. Again, one has this method of descent. Basically say that if first of all you choose that there's a multiple of p which is sum of square mp, and you can gradually go down to actually prove that the multiple p itself is going to sum of 4 square. There is a method of descent. All right. So this case again, we are interested on this formula of R4 of n, namely this is the number of way you write n as sum of 4 squares. And there are the residual due to Jacobi that R4 of n is equal to 8 times the sum of the divisors, d divides n, but we take those divisors which are not 0 modulo 4. The 4 do not divide d. And using this formula, you can see that given any number R4 1, R4, we can compute this number. Just look the divisors. So we see that for this R2 of n and R4 of n, there are similar looking formula, but for R3 of n is completely different kind of formula, which are basically difficult. Okay, and just to remark in the previous case, for this R3 of n, capital R3 of n, we are looking this h of n. So there is something called class number formula due to Dirichlet. He expressed this hn in terms of special values of these Dirichlet L functions coming to the pictures, and this formula also quite a way one can write the hn replace in terms of some other kind of functions, in terms of basically coming from Jacobi sums. All right. Okay, so one can compute this R2 and R4 easily compared to R3. That's what I want to emphasize on that. Now, this is something where I like to point it out that we are interested on the sum of 4 square x square plus y square plus z square plus w square, and any quadratic forms. Okay, we're looking these forms x square plus y square plus z square plus w square, and where all natural numbers are sum of 4 square. So basically, if you take this x square plus y square plus z square plus w square, you vary this x, y, z, w, then you can get all the natural numbers. Also 0 you can commute out from here. Okay, so similar kind of question you can ask for any quadratic forms. Okay, for example, with coefficient. Earlier you were taking a, b, c, d, 1, 1, 1, 1. But now you can take this quadratic form ax square plus by square plus cz square plus dw square, and you can ask that for which a, b, c, d, okay, can you find all the a, b, c, d for which these quadratic forms or this assumes all positive integers. Okay, and Ramanujan in his one of these important paper, he found 54 quadratic forms of this type this, and he found 54 quadruple a, b, c, d for which they are all the inverse. They represent all these positive numbers. Basically, something called universality. This quadratic form are universal. Basically, depend all these positive integers. Okay, they are similar theorems to Lagrange, but the proofs Ramanujan gives is elementary way. But the number of way one represents is not given there. Then one can find out that way one can find out this formula of R4 R with this particular quadratic forms given n. How many? Given n and given ABCD, those 54 ABCD. So one can ask that what are the formula for the number of way one represent this n in terms of this particular quadratic forms. Okay, so namely find the representation formula for the I'm putting this quadratic forms ax square plus by square plus cz square plus dw square, and putting this given ABCD and given n, find the number of way we can write n as these particular forms. So one can consider these questions about sum of 5 square or more square or any quadratic forms, any good quadratic forms. Good means I'll tell. And how to answer these questions? Okay, there are elementary way, but elementary way after some time may not work. And basically, you are going to use this theory of quadratic forms. And what I want to say quadratic forms is basically let's just I have to describe in a very using this kind of use of complex analysis. Again, come to this one can use in the theory of numbers. And basically, modular forms are special functions that are analogous to the trigonometric functions sine, cos, tan. They are all periodic functions. And modular forms have periodicity plus extra symmetries that are essentially unchanged under the large group of substitutions. So it has its periodicity, but some other group come into the pictures, and they basically has symmetry with respect to those groups. And the symmetry allows these modular forms to write as a Fourier series, something like A and Qn, and Q is going to be 2 pi z. My function is on z, and I'll define properly in the next slide. And the coefficients ans, they are actually interesting to the number theorists. The ans coefficient of modular forms contains information about number representation of integers by positive definite binary quadratic forms. That's what we are talking about today. And also this coefficient gives class numbers of quadratic fields. And this can be value of some combinatorial functions. Also, this count in some situations count the number of points of our finite field FP on certain varieties like elliptic curves, etc. So there is a famous quotation by Martin Eckler. Basically, he said there are 5 fundamental operations in mathematics: addition, subtraction, multiplication, division, and something called modular forms. So basically, the modular forms appears more or less in all part of mathematics. That's what basically this quotation means. All right. So let me define what do you mean by a modular form. Okay, so we say a modular form of weight K for this group SL2G. SL2G means set of all 2 cross 2 matrices, all integers entries, and the determinant equal to 1. And we know that this SL2G act on this complex upper half-plane, that's denoted by H. Okay, and this by the Mobius transformations, Z goes to AZ plus B by CZ plus D. So this SL2G act on this complex upper half-plane. And we are looking for some analytic functions on the upper half plane, which are some kind of invariant, not exactly invariant. If K equal to 0, you get invariant, but we are looking for some general things. So basically, f of AZ plus B by CZ plus D is equal to CZ plus D to the power K times f of Z for all A, B, C, D in SL2. These are I'm talking about the extra symmetry with respect to this large group of substitution. Means we have a group, and with respect to these group actions, the functions behave like this. And this function f of z admits a Fourier expansion of the form f of z equal to summation a and qn. Q is equal to e 2 pi z. And I'm assuming that all the Fourier copies of these things start from n bigger than equal to 0. Okay. And the interesting fact is that the space of modular forms given a weight k, and the space of modular forms you can make a vector space over complex numbers. Namely, f is a modular form of weight k, g is a modular form of weight k, then f plus g also a modular form of weight k. And you can multiply any complex numbers, the scalar multiplications. Again, if f is a modular form of weight k, you take a complex number lambda, then lambda f also is a modular form of weight k. Okay, so the space of modular form is a finite dimensional, it's a complex vector space. And the important thing here, one can use again complex analysis as a corollary of residue theorems to show that to see this is a finite dimensional vector space. So one can do all sort of linear algebra that come from finite dimensional linear algebra. All right. So let me give one example, and basically this example is good enough to construct all of the examples. So basically you are taking k bigger than 4 because of this convergence region. And we define this ek of z is equal to 1 by 2. This is some kind of normalization factor. Basically, this is the sum over this m comma n belongs to z2. M and are integers, not both 0 together. And I'm taking the GCD of m comma n is equal to 1. And I'm summing over this 1 by mz plus n to the power k. Okay. If you look at the definitions, and we know that the SL2Z is generated by this translation matrix z goes to z plus 1. And the other one, the inversion matrix z goes to minus 1 by z. And one can see that the EKZ behaves very nicely with respect to these matrices. And using those 2 matrices, one can prove that these automorphic equations, as I told you here, one can prove this EK of AZ plus B by CZ plus D equal to CZ plus D to the power K into EKZ. And just to test for this, there's enough to test for this translation matrix. Z goes to Z plus 1, and other matrix Z goes to minus 1 by Z. All right, and basically we are summing over relatives, and you are doing the transformations. Z goes to Z plus 1, then this basically stands something like mz plus m plus n, and basically the mz plus m, the m again summing over the second part, mz plus m plus n. Since m and n are varying, that is become some of the same lattice, and it because of this invariant of the lattices, you can get EKZ plus 1 equal to EKZ. Similarly, you can get for EK of minus 1 by Z equal to Z to the power K times EK of Z. And the interesting fact one can use again by using this complex analysis that EK of Z has Fourier expansion. EK of Z is equal to 1 minus 2K by BK. BK are the boundary number, which are rational numbers. And the Fourier coefficient I was talking about, this looks like the A and Qn. The A n is basically the number theoretic function. Sigma k of n is basically sum over d power k and d running over n. So given a k, given a n, you take all the divisors of n and take the all kth power and sum it off. Those sigma kn appears as Fourier coefficients of this adjacency. So that's the first link with this this complex analytic functions and the number theory. Basically, this sigma, this is called some divisor function that appears as Fourier coefficients, nth Fourier coefficients. And if you want to write it down for certain k, for example, E4, we have this 2k by bk becomes minus 2k by bk becomes 240, and you get this sigma 3 and k here. Here is k here, that becomes k minus 1. So E4, you get 1 plus 240 times sigma 3 n qn. Similarly, E6, you get minus 504 sigma 5 of n qn. Similarly, E8 n we get from here. Okay, so one can prove certain other things, namely these modular forms are something like, if you take all modular forms, this becomes something called graded algebra. Namely, you have a modular form weight k, you have a modular form weight L, then the product is a modular form weight k plus L. So it's kind of, it has something like graded structure in the for this modular forms. So you can see nicely that E4 square is something like E8. If you have some kind of dimension formula, both the dimension 1, then E4 square equal to E8. So you can get some relation among the sigma 3 convolutions with sigma 7. Okay, so since we are starting with this sum of squares, let's see how this is related to the complex, the modular forms. So you consider the theta series, namely theta z is equal to q to the power m square. Remember, q is something like e 2 pi I z. So it is from summation q m square. M is weighing of integers, and if you write this because plus m and minus m give the same square, we get a something like 1 plus 2q plus 2q4 to q9. So this is how it looks like in terms of q. And theta z has the following symmetry that one can, okay, theta z plus 1 equal to theta z, that's one can observe easily from here. And but the other symmetry, theta of minus 1 by 4z equal to root 2z by I over theta z, one can prove using something this using Poisson summation formula. And what you can see from here that this theta z, if you take theta to the power 4th power, okay, then this particular thing you can write it easily, something like 2z to the power square. And basically what you get that theta z is a modular form of weight 2 for not for SL2G, but one can define something called modular form for congruence of group gamma 04. They are basically those matrices A, B, C, D, and with 4 divides C. Okay, this kind of matrix you get symmetry for this particular group. And one more observation I would like to make it here that theta 4z, if you write theta 4z, remember theta z is nothing but summation of qm square, m is varying over that. Okay, if we multiply 4 times, okay, you get theta z, theta z, theta z, theta z 4 times. And if you write as individual product, I write a product of 4 terms like that, q of m1 square plus m2 square plus m3 square plus m4 square. All right, this is the product of all theta 4. But interesting thing, they use them on the right hand side. Okay, now fix a n. Okay, you fix a n. Suppose n appears as sum of 4 squares. Okay, here this is equal to n. So how many times it appears as sum of 4 squares? Can you count those number of the functions? This is exactly as number of way n written as sum of 4 square. Because if you write this will be n here, so basically we are counting number of m1, m2, m3, m4 over integers. So the m1 square plus m2 square plus m3 square plus m4 square equal to n. So exactly the coefficients are 4 of n, namely n as written as sum of 4 squares appear as the Fourier coefficients of this particular modular forms. Okay, and basically what you prove that the theta 4 of z is a modular form weight 2. As I said, this becomes, if you take modular form weight k, you keep on multiplying, you get modular form for the higher weight, basically multiple of that. And we have this, let me give you a small brief, a proof of this fact. Okay, so this modular form of weight 2 for gamma 04 is a 2-dimensional vector space, then one can prove. And one can find a basis using this E2. Okay, E2 is we define like here. Okay, so if you go back to the definition of EK, I defined sometime before, that's not defined for k equal to 2 because of this convergence problem. So one can define this E2 is of this kind, 1 minus 24 times sigma n. Sigma n means sigma 1 of n, namely sum of divisors of n. And one can create a basis for this space of modular form weight 2 of gamma 0, 4. And we can have a basis of this kind, E2 of Z minus 2 E2 of Z, and E2 of 2Z minus 4 E2 of 4Z. And we know this is a finite dimensional vector space. Suppose you know the dimension, that's equal to 2. Then this theta to the power 4Z, this is a modular form weight 2. So I can write in terms of this basis. So I have these particular coefficients, minus 1 by 3 and minus 2 by 3. I can find these coefficients just comparing some of these past 3 Fourier coefficients. And if I write down, this becomes theta 4 of Z equal to 8 times minus 8 times 8 by over 24 E2Z plus 32 over 24 E2 of 4Z. Now write this E2Z in terms of this Fourier expansion, 1 minus in place of Z, put like that, in place of 4Z, something like sigma n by 4 q n. And if we equate both sides, the Fourier coefficients, on the left hand side, I got R4 of n. On the right hand side, I got exactly 8 sigma n minus of 32 sigma n by 4. See the 24 and 24 here, there's 24 cancels. So 8 sigma n minus 32 n by 4. This exactly is equal to 8 times summation over d divisors of d divides n and 4 does not divide d. Exactly the formula of Jacobi. Okay. So this method is interesting here because you can apply this method any general nice quadratic forms. Basically, your R4n, you get using this method, you can create something called theta series. And using this finite dimensional property coming from these modular forms, you can find nice basis. And somehow you can use this basis to find this Fourier coefficients R4n in terms of this formula, in terms of this coefficient on the basis. Okay. Basically, how do you prove that? And in R4, and you can see that R4n, this is just a counting function. This is always bigger than equal to 0, or for R4n, this is always bigger than equal to 8. So this number always bigger than equal to 1. Namely, all the numbers can be a sum of 4 squares. So basically, what do you prove this theorem of Lagrange and this Jacobi, both theorems you can prove together using the theory of modular forms. And what is interesting here that this method can be applied in different situations. For example, let me see from R8. So I want to write sum of 8 square given a number n. I want to write n as sum of 8 square. So let's look at this R8n. So you can write this summatory functions, summation over L comma n belongs to n naught. N naught means n union 0. And we're looking for L plus m equal to n. And given this L, how many ways you can write L as sum of 4 squares? And for every representation, I am counting once. Similarly, for m, I have these representations sum of 4 squares. I'm counting every representation gives 1. So this exactly is splitting L given a n. I'm splitting as L plus m. And now looking this L is sum of 4 square, m is sum of 4 square. So L plus m is sum of 8 square. So if you write like this, then you can get some interesting consequence. Okay. So if n equal to 0, LMN can be 0, one of these things can be 0. So I'm putting this R4n, R4 of 0. And for other than zeros, I have this number L comma n belongs to n, L plus m equal to n. So R4L, R4m, L plus m belongs to n. Now I use the formula as I got earlier, R4m equal to 8 sigma n minus 32 sigma n 4. So if I multiply here, okay, and I put in the R4n formula, so I got this particular formula for R4 of L. And R4 of m, I get this particular formula for R4 of m. And my sum is running over L comma m, L plus m equal to n. This is the condition I have. So if I multiply everything now, I get these expressions here. Just I multiply 8 sigma L, 8 sigma m, and just I multiply in terms of that. I am multiplying everything. I got some of these terms like this. All right. And what is interesting here that if I can compute this kind of sums, okay, given a n, I'm writing sigma L, sigma m, L plus m equal to n. What is sigma? Sigma is the number of sum of the divisors of n. Sigma m is the sum of divisors alone. I'm taking this convolution sum of this kind. If I write down all this sum in somehow, then I can get a formula for R8 of n. So given an expression of R4 of n, I can create a formula of R8 of n. Okay. So that's what it says. If you can compute this convolution sums in terms of this somehow, then you can get a formula for R8 of n. And one can compute this convolution sum by inventive way. Elementary way means not using any kind of complex analysis or any kind of quadratic forms. You can just use elementary number theory to compute. There are a way of doing that. Also, one can use modular forms, and one can see that using some way, we can find this formula R8 of n equal to 16 times sigma 3 of n minus 32 sigma 3 n by 2 plus 256 times sigma 3 of n by 4. Okay, so basically, given a formula from R4 of n, I can compute a formula for R8 of n just using this trick of convolution sorts. And let us go to the general theta series. Okay, so we are not only interested in the sum of squares, namely x square plus y square plus z square plus w square, or you can consider any positive definite quadratic forms. Okay, positive definite means quadratic forms is always takes positive values. Then you can associate this theta series the same way, namely you can sum it over this a1, a2, ak. Suppose there are k many variables. Okay, so q to the power k a1, a2, ak, and then you can write as you see from the sum of 4 square discussions, you can write this as 1 plus rq of n to n, and the rq of n exactly the number of way we can write n as this representation by q. Okay, and there's it's a well-known result is say that this is a modular form weight k by 2, but for some subgroup of SL2G, not necessarily for a whole group, but for some subgroup SL2G. So if one can see, one can find some nice basis or using this thing, then one can get nice formula for this RQ of n. And for example, I'm giving some of the example like R12 of n. So 12 of n means number of way we can write n as sum of 12 square is exactly some of this formula like 8 sigma 5 of n. The sigma 5 means we are taking the fifth power is for each divisor and summing it off. And sometimes you get something like 16. You have the sigma functions, and you have these some functions which are something called cos forms. Okay, so basically, given any modular forms, we can write into two ways. Okay, there is something in the space of modular forms. We have this part something called Einstein series. I defined sometime before, and other part something called cos forms, cos part, and basically the Bn are basically the cos parts, and which you can write in terms of Q series. Okay, of this form, this infinite series is just written as a product formula. Write there in terms of the summation formula nth coefficient as Bn. And similarly, if you are interested for sum of 24 square, and actually this is a formula due to Ramanujan. Okay, so 24 squares given n, you want to write n as sum of 24 squares. You can either use this method of Q series, or you can use this method of convolutions to get a formula for R24n, namely n it in a sum of 24 squares. And this is exactly the sigma 11n, and come into the picture with various coefficients. And then another interesting forms that appear in the formula, namely Ramanujan tau functions. Okay, let me define that here. So this is basically is a cos form of weight 12. All are weight 12 form. So whenever we're considering 24n, so we're taking a quadratic forms of 24 variables. So the modular form of weight k by 2, that is 12. And this, because of this 12, there are Einstein series of weight 12, and there are cos form of weight 12. Basically, the tau function come into the picture. So all these things of sum of even number of square can be dealt with this way, and one can get the formula for this number of way represented by sum of 24 square or 12 square. Okay, so what is this Ramanujan tau functions that appears here? Let me just give some how to one define. Okay, the infinite product, you take q product 1 from 1 to n from 1 to infinity 1 minus qn to the power 24, and write this product in terms of summatory functions, something like summation tau n qn. And tau n is called the Ramanujan tau functions. And the first p value Ramanujan computed is tau 1 equal to 1, tau 2 equal to minus 24, tau 3, etc. And you see the tau go very, very fast. And what you want to see in the case that this the form I'm writing here, summation tau n qn, is exactly is a coefficients of some cos forms, namely E4 of Q. E4 is this Einstein series of weight 4. I'm taking the third powers to get a modular form weight 12. And similarly, I'm getting the E6, that's a modular form weight 6. I'm taking the square, you get a modular form weight 12. And both there's constant coefficient 1. So they get cancelled. So there is no constant coefficient in both in the difference. And modular forms with the A0 term is 0, that we call the cos forms. And we are dividing by 1728 to get it this the product to be, we are just normalizing it so that tau 1 becomes 1. And this is a cos form weight 12 and has the Fourier coefficient tau 1. So there are interesting Ramanujan conjecture the following properties about tau n, namely tau n is multiplicative, namely tau f mn equal to tau m times tau n if GCD of m comma n is equal to 1. And so it is enough, if you have this conjecture, then it is enough to consider this tau of prime powers. And for the prime powers, Ramanujan conjecture that tau of p power n plus 1 is nothing but tau p times tau p of n, p to the power n, minus p to the 11 tau p n to the n minus 1. Also, he conjectures this bound for tau n, namely tau n modulus is sigma 0 n, and the number of divisors of n, times n to the power 11 by 2. And these identities, these two conjectures first were proved by Model in 1921. There is something called Hecke theory coming out from these relations, which are proved by Model, and later Hecke developed the Hecke theory. And the third conjecture was proved by Deligne in 1974, and it's a kind of consequence of Weil conjecture, and for which he gave the Fields Medal in 1974. And there's another famous conjecture related to tau n. I like to state here that Lehmer conjecture that the tau n is never 0. Yes, and Lehmer himself verified something like this big number in 1949. And there is a recent work by the Derricks, Hosey, and Zhang. They prove using this computational number theory, they verified that this conjecture is true up to n equal to something like 8 to the power 10 to the power 25. This many numbers, this conjecture is true. Still, this is not a theorem yet, but one can kind of expect this theorem to be true. Namely, tau n is never equal to 0. Okay, so this is the story about tau n. But so far, we have considered up to all the even power, namely 2, 4, 6, or 8. And we see that sum of 3 squares, as you see earlier, is basically quite difficult, and one has to completely handle the 3, 5, 7, 9, 11 in a completely different way. And those are kind of complicated formula, and it needs more ingredient to prove those kind of things. All right. So let me just end with this Hardy's observation on Ramanujan. Okay, the most romantic figure in the recent history of mathematics, Ramanujan was in a way my discovery. I did not invent him like other great men, he invented himself. But I was the first really competent person who had a chance to see some of his work. And I still remember the satisfaction that I could recognize at once what a treasure I had found. And my association with him is one of the romantic incidents of my life. This is how Hardy respected Ramanujan. Okay, and I'd like to thank you for your kind listening my talk, and you have any questions, certainly I can answer some of the things. Thank you very much.
Thank you, Sahu sir, for this nice talk. Anybody has any questions? You can unmute yourself and ask. Okay, sir, maybe you can tell some references.
Yeah,
maybe
hello?
the Graswald book and this Koblage one.
Yeah, there's a nice book by Groswell, basically representation of integer sum of square. This is one of the kind of the interesting book in this theory. Okay, and for the modular form part, there is a part of modular form in the same book also. But there are nice book on modular forms, Koblage or Sayre on arithmetic book. They are quite very nice introduction to modular forms.
Okay, anybody has any questions? Let me check the chat box. Okay, if there is no questions, let's thank the speaker.
Thank you very much.
Thank you, professors.
Okay, Kiran Bhaiya, you can take over.
Yeah, thank you, sir, for this nice talk. It's really interesting to always listen to number theory. It's one of the purest form of mathematics. So, yeah, thank you very much, sir.
Yeah, thank you very much. Yeah. Shall I stop sharing, Kiran?
Sure, sir. You can stop sharing. Thank you, sir. We'll have a take a break and we'll go to the next session.
Okay. Okay. Thank you very much, Kiran. Thank you very much.
Welcome, sir. And I hope you will continue MTTS.
Yeah, sure, sure. Yeah.
Thank you.
Kiran Bhaiya, can you give a short intro about next session and when it is starting so that people will know?
Yeah, so the next session will start at 3, and it's quite different from the ones that we have had till now. So it's a panel discussion. So we have 5 panelists, and the panel, just a minute. So we have the topic is mathematics beyond the mainstream classroom. And the panelists are Professor Geetha Ventakaraman from R.Ambedkar University, Delhi, Professor Tulsi Srinivasan from Azim Premji University, Professor Ajit Kumar from ICT Mumbai, Professor Chandrashekaran from Central University of Tamil Nadu, and Professor Krishna Hanumanthu from Chennai Mathematical Institute. So please do join at 3, and right, we'll listen to the panel discussion, what they have to say on the topic mathematics beyond the mainstream classroom. So it's quite relevant in the current era where you are living, since truly studies have gone beyond classroom, right? So we'll start in another 5 minutes.
It is the same link for your information. You can stay on the call or go back and come again. So we'll start at 3.
We'll start at 3. This is the same Zoom link, and right. Hello, Ajit sir.
Hi, Kiran. Hi, how are you?
I'm fine, sir.
Yeah. Good. So, how is it going?
Yeah, it's fine.
Hi, good afternoon, Mr. Geetha.
Hi, Ajit. Hi. How are you?
How are you? Yeah, I'm good, good. Nice to see you.
Good way to be spending a Sunday afternoon, no?
Yes. Right. So, how is the pollution in Delhi?
I'm trying not to head out.
That's the best way to explain. Hi, hello, good evening, sir.
It's so interesting to see all our old friends.
Yes.
Hi.
How are you?
Fine, going on.
Are you now in Chennai only, or
I am only in Chennai. I have left my Bombay job a couple of years back.
Okay.
Yeah. Waiting for a nice, interesting panel discussion.
I hope we don't disappoint you. I guess we have a couple of minutes more, right?
Yes, yes.
Yeah, take off.
So, all the panelists are here or no? Not yet. Kiran? Yeah. Hi, Krishna.
Hi. Yeah, hi, Ajit.
Tulsi.
So waiting for Chandru, sir.
Okay, okay.
Hi, good evening all. I'm here.
Oh,
Hi,
Maybe
Chandru,
yeah,
you're a level, MTTS level low. That's why we
yes,
couldn't take
that's me.
it. Okay, I guess so.
Just a minute. I don't know.
Yeah, you can just rename yourself.
Somehow I could not rename, sir. I'm in Linux machine.
Or they can ask a host to rename you.
Yeah, can you do that? Just rename MTTS level 1 as Chandrashekaran.
Let me try, sir.
So even host is unable to rename you.
We will make Sir a co-host, and I think by then he will be able to read himself.
Yeah, I will
Okay.
try that.
Yeah, I just doing it. So can you try now, Chandru, sir?
Even then, it's not allowing me.
I think it should be changed before coming in because of some
Yeah,
settings.
can I just log out and come back?
Sure, sir. Sure.
Yeah.
Okay, so learn will start once Chandru sir joins.
Sure.
Sir is joined.
Yeah.
Over to the panel discussion team, Saintani, Priya Kaveri, and Jaskaran. You guys can take over.
Hello, I hope I am audible.
Yes,
Okay.
please.
Yes. Okay. Good afternoon. I welcome all of you to today's panel discussion. So myself, Priya Kaveri, I'm currently second year master's student at IIT Madras. So I'm one of the moderators of today's panel discussion. We have two more moderators. Let me introduce them. Jaskaran, he's first year master's student at IIT Bombay, and Saintani, she's a first year master's student at RKM. Okay, so now I would like to invite Jaskaran to give a brief overview about today's panel discussion.
Thank you, Priya. So basically, if a student is pursuing graduation in mathematics, what are the odds that he's aware of the different routes or career paths he can take? Some of them don't even have enough information regarding what course could be suitable for them. Many of them even take a path chosen by many others, like any mainstream path. And moreover, in last 2 to 3 years, the effect of pandemic has been adversely visible in all aspects of academia. With minimal or no guidance, many of the students are disoriented in their academics and often choose other careers just because of lack of guidance. Moreover, they have a huge pile of confusion left out to be sorted. Who can they look up for the answers? I think today we would be able to answer the same.
Hello everyone, I'm Srinivasan. Today we are extremely fortunate to have with us 5 distinguished panelists as the panelist of this discussion. We have with us Professor Chandrashekaran from the Central University of Tamil Nadu, Professor Krishna Hanumanthu from Chennai Mathematical Institute, Professor Ajit Kumar from ICT Mumbai, Professor Geetha Ventakaraman from the School of Liberal Studies, Dr. R.Ambedkar University, Delhi, and Professor Tulsi Srinivasan from Azim Premji University. Let me tell you the format of this event. In the first half an hour of the discussion, we will hear from our panelists about their story of pursuing a career in the field of mathematics for about 5 minutes each. We would request them to outline what prompted them to choose a career in this field and what they faced as a fresh undergrad. We would like to hear from them about the exposure they received in their undergrad days, and also tell us if hobbies and extracurricular activities were a part of their journey and whether that helped them in hindsight. The next hour and a half will be a question and answer session, and if time permits, we shall open the floor to the audience for questions. So we would like to commence this event with Professor Chandrashekaran. Professor Chandrashekaran is currently associated with the Central University of Tamil Nadu as an assistant professor. He is also associated with MTTS for a long time. He completed his graduation and masters from Ayyanadar Janaki Ammal College, Shivakasi, and received his PhD from IIT Madras. Professor Chandrashekaran, I would request you to.
Yeah, good evening, all of you. So the question is how I was motivated to choose a career in mathematics. Mine is not a very different from any other. In my those who are coming from South Tamil Nadu, in fact, many parts of the other country also. See, I had this idea somehow when I started from 10th standard. I completed 10th standard, I went to 11th, and I found that this integration and differentiation were introduced, and I failed. So far, there will be a lot of computations, and then now there is some methods have to be followed, some formulae have to be remembered, and then I failed. So later, somehow I managed to understand how these formulas can be derived. Okay, when they introduce this substitution method, various methods of integration and other things. So the important part which I learned at the end of 12th standard is, if I choose mathematics, I don't have to remember much. That is, whatever you learn, if you have understood some way in which it can be done, you can recreate it. Okay. So as everyone was those days dreaming about engineering, I could not secure enough marks in 12th so that I can secure a good college of my choice, an affordable college also. So then I was forced to choose some science streams, and I chose mathematics because I don't have to remember anything. I suspected, I assumed that. The other thing is, I don't have to maintain any record notebooks. I'm good at doing lab work and other things. So physics and chemistry labs are very good for me. I can do very well, but I don't want to do that. So I went into mathematics. And my aim was after BS, I want to go out and do some job, which I had already worked in some workshops and other places. I know something. I thought I will end up in that place and I can do something. So I learned some other thing like photo lamination, etc., which I can continue. But unfortunately or fortunately, I, like many students, those days the information was very less. Actually, I could not get it, but somehow I got the information about MTTS. I got information about INSA summer fellowship. I applied, and what happened is they selected me. So like even now the trend is, if somebody is selected for INSA summer fellowship and somebody is selected for MTTS, the student generally want to go to INSA. The reason is that's a 2-month program and MTTS is 1-month program. The same kind of idea I had. I went to summer fellowship. I went to Professor Kannan. How I went to Professor Kannan at HCU is, the name is Tamil name. So I thought, okay, I can be comfortable there. So I went there. And then in the first day, I told him why I came, what I did. And I also told I was selected for MTTS. Then what he said is, more than this, that will be useful. You go there and I will write to INSA, and you can also write, they will permit you to continue the program after you come back from MTTS. So that's how I landed in MTTS. And this MTTS was something, it taught me how to learn mathematics. So far, whatever I have been understanding, mathematics is completely in a different way. It's a kind of, there is some understanding, but there is so much of irregularity or some kind of gaps in my understanding. So all those things have been corrected there. So that means what I was trained for is, given a book or anything I want to read on mathematics on my own, I was equipped to do that in MTTS program. Later I went back to my college. I had everything, the whole attitude of me reading a book, what I understand from that, everything has changed. So that put me in proper track actually. And in fact, even I can see that difference when I went back from MTTS once again to that INSA summer fellowship also. So that's where I noticed that I could read the same subject which was given to me at that time in a better way. I could identify my own mistakes, what I did earlier, and all. So many things it has changed. So in some sense, MTTS played a crucial role for me to further continue in MSc in mathematics. And in fact, I got fellowship to do my MSc from NBHM. I wrote that exam. I attended my interview at HRI. These all happened after MTTS. So then I got a fellowship for my PhD also from NBHM. So many things happened, and then I stick to mathematics and I continue. And I'm doing as a teacher now in a university. I hope, do I have to say something more? I think that's fine. Thank you.
Thank you so much, Professor Chandrashekaran. We would now like to request Professor Ajit Kumar to share his story. Professor Ajit Kumar is currently a faculty at the Institute of Chemical Technology, Mumbai. He is also the managing trustee of the MTTS Trust. He completed his master's and received his PhD from University of Mumbai. His research interests include optimization and statistical techniques, differential geometry and analysis, mathematical pedagogy, and the use of computer-aided tools and mathematical software in mathematics. Ajit sir, over to you.
Thank you. Thank you. First of all, I thank the QueryLeaf team for organizing this panel discussion. And really very heartening to see this team is doing very wonderful job. So first of all, a big compliment to all of you. for doing this fantastic job. So first of all, about me, I think why I'm in mathematics, that completely I owe it to MTTS. Possibly I was again lucky enough to be selected for MTTS and in 1995, and after that everything changed. Of course, when I was in my school or in the college, I thought I'm reasonably good at mathematics. Maybe that is what I thought, but of course I found out that when I came to MTTS, that MTTS is the one which made a lot of difference to me. And as I said, whatever I am today, it's mainly because of this MTTS support. So I think one of the things that I would like to say, and I generally tell the students, whatever difficulties you have, it doesn't matter. If you love to do something, continue doing that, and I am sure everything else will follow. There will be people to help you. And in my journey, a lot of people have helped me in spite of several difficulties and other things that I had coming from a very small village in Bihar. And of course, one of them is none other than Prof. Chandrashekaran, who has helped me quite a bit. And so regarding the topic of this panel discussion, I'll say something more, and whatever thought I have, that I will tell later. Okay, so that's all from me, I think. Over to you.
Thank you so much, Professor Ajit Kumar. Moving on, now we would like to invite Professor Krishna Hanumanthu. Professor Hanumanthu completed his graduation and master's from Chennai Mathematical Institute and got his PhD from University of Missouri, Columbia, under the guidance of Professor Dale Kotowski. Prior to joining CMI in 2011, he spent 3 years as a postdoc at the University of Kansas Lawrence. His research interests include algebraic geometry and commutative algebra. He is currently working as an associate professor at the Chennai Mathematical Institute. Professor Krishna, I would request you to take the stage.
Thank you very much. I'm very happy to be here, and this kind of thing is new to me, so I'll see how it goes. So thanks for inviting me. I'm looking forward to interacting with all the participants. So very briefly, I want to talk about my experience in studying BSc. So as I think this applies to everyone, and as has been mentioned, I was interested in maths from childhood. So there is this, in school, people recognize this, right? All of us have this experience. This person is good in maths. And every school has, or class has a few such people. So I wanted to do something related to mathematics. But as I grew up, maybe finished my high school, I also developed some kind of maybe phobia or dislike for engineering. So I wanted to be different from most of my classmates. So I wanted to do something more math focused. So there were not too many options at the time. This was 1998, and CMI was one of the options. So I came here, and it was a very small batch at the time. We were around 6 people in our class at the time. So it was very different from anything that I knew before, because it was, first of all, only 6 people. That was very unusual. CMI was in a very small place, and all the people were, knew each other. But in terms of mathematics, it was very different, because, we learned how to solve problems using some methods till that point, but then we were taught the concepts behind each problem or each subject, and go more into principles that make everything work. So it was a struggle to begin with, though I realized, I knew that I was interested in maths, but it was not really clear to me what mathematics was till I went to CMI. So I learned, how to study, what are the things to focus on, what are good books in each subject. So that was my experience. It was at some level like a typical BSc experience, though because we were only 6 people and with not much extracurricular activities or any other things happening. But we were in Chennai, so there were many things that we could do. But and then to be frank, I didn't know what I was going to do after my BSc. So I just liked mathematics. So I came to CMI because that was the best option for me among the options I had. And then slowly one learns that these are options. One can do MSc, then one can do PhD, and there is this option to be an academic and do research and teaching in mathematics. So that I learned over time. And then I was fortunate that everything worked out. And then I finished, BSc, MSc, PhD. I then came back to CMI. So that is pretty much all. I mean, I was interested in maths, really. That is the main motivation. I didn't have any deeper understanding of what the subject was or what one can do with it. So based on that, I came here and then sort of learned what to do at each stage and continued in the same path. So I think I'll stop with this for now, and maybe as we proceed further and there are more questions, we can discuss more. Thank you.
Thank you so much, Professor Hanumanthu. Now, we would like to invite Professor Geetha Ventakaraman. Professor Geetha Ventakaraman did a BSc Honours in Mathematics at St. Stephen's College, University of Delhi. She stood first at the University of Delhi BSc Honours Mathematics. She was awarded an in-lakhs scholarship to read a second BA Honours in Mathematics, which is equivalent to Masters at the University of Oxford. Her doctoral degree DPhil is from the University of Oxford. A Burton Senior Scholarship from Oriel College, University of Oxford, supported her research for the doctorate. Professor Ventakaraman's doctoral work was in group theory. She researched questions regarding the enumeration of finite groups. Professor Ventakaraman continues to work on various aspects of group theory. Apart from her interest in group theory and related areas, she is deeply interested in popularizing mathematics, mathematics education, and issues related to women in mathematics. She is currently a professor at the School of Liberal Studies, Dr. R.Ambedkar University, Delhi. Geetha ma'am, I would now request you to take the stage.
Thank you, Sir Anthony, and thanks so much to the organizers of Curry Leaf for asking me to be part of this panel. I will preface whatever I say with the following statement. I think I'm the most ancient out of the panelists today. I started teaching in 1993 after I'd finished my PhD. So I've had, I suppose, I've seen several generations of students. So my understanding has also changed over a period of time. But this part of the panel, we are supposed to talk about how we got interested in maths and how we came to do what we are doing. So I'll start by saying that I was always, I liked maths, and I think I was good at it at school. My father had done mathematics. He'd studied in Vivekananda College in Chennai. He had done maths honors in those days. And my mother had done physics, but she claimed that she only did physics because her elder sister had done physics and they didn't have too much money to buy other textbooks. So she was also told, you also do physics, you use those textbooks. But she liked maths a lot. So my family, there are lots of teachers. My grandfather was a teacher and so on. So that's the kind of background that I come from. And in school, I really enjoyed maths. But I think till middle school, I wanted to be a brain surgeon. So my aim was that I would grow up and become a brain surgeon. And I'm a standard when one of my classmates, she talked about her cousin who was doing MBBS, and she talked about the huge number of books that they had to read and literally memorize. And while I had a good memory, that's definitely not what I wanted to do. So I think that was the stage when I decided that there's no way I'm going to be a doctor of medicine, at least, because it would involve too much of memorization. And in school also, I liked, I liked geometry a lot, particularly when we were learning about, congruence, similarity, and the whole idea that you were given some rules or axioms, so to say, and then you had to apply them and solve a lot of problems. That was the kind of thing I really enjoyed. The other thing that I remember from school most of all was, this was when I was in, I think I had a cousin who was a year or 2-3 years older, and she had just studied quadratic equations in school. And she came and told me, showed me this thing of how to complete squares and find the roots of a quadratic equation. And it seemed like a piece of magic to me. So these were things that I really enjoyed in school. But like everyone else, I think of my generation, and particularly also because I had a older cousin brother who was studying engineering at that point at IIT Chennai, IIT Madras. So I used to be in great competition with him, whether it was in the amount we ate or whatever he did, I had to do better. So so then I also decided that I would take the entrance exams for engineering. Those days we had Agarwal coaching class correspondence material. I don't think I ever bothered to go through them very much other than the maths, because I actually was not terribly good at physics, and chemistry was fantastic. I liked it, but not physics so much. Finally, I did get into BITS Pilani after my 12th standard, but I don't think my parents were very keen on sending me away. We were in Delhi at that time, and and since I really liked maths, I was getting admission. I got admission in Stephens in maths. I also got admission in physics and in chemistry, but I chose to do mathematics. When I joined college, the first year we had was a continuation of school. We did basically coordinate geometry, and we did some amount of, we did things like successive differentiation. There was some more we learned about integration, but mainly methods, not really delving into why these things were happening and so on. So first year, I still thought, I would maybe go for an MBA after my undergrad, or those days masters in computer applications was also a very popular choice. So those were my two options at the when I first joined college. But second year we did abstract algebra and analysis, and that was it. I just fell in love. I didn't want to do anything else with my life other than do maths at that point. And I think my parents were quite upset because of their thing was, you'll do maths and then what will you do? You'll become a teacher. And I don't think either of them wanted me to take up teaching as a profession. But I mean, as I said, I fell in love with mathematics, and then my course was set. While I was finishing college, I had this opportunity to, I mean, in fact, I'd applied to TIFR as well and had been called for the interview. But again, I'm an only child, and my parents were very worried that if I'd go to TIFR and get admitted directly to a PhD, not be able to do it, then what will I be left with? So this whole thing of wanting to have a degree at the end of whatever you do, which you're sure to get, was something I think was very important to them. Eventually, I got a scholarship to go to Oxford, and there, I mean, I came from a system in Delhi University where you looked at 10 years of question papers. You pretty much had an idea of what kinds of questions would be asked. And I went into Oxford knowing that I would have exams at the end of 2 years, and that there are questions often there which sometimes lead to research. And so it was a very scary feeling going there and wondering whether I would be able to cope with the system there. And I'll just share one small bit and then I'll stop. I reached my college, and every student has a little post box called Pigeonhole. I go there and I open it, and I mean, I see a lot of sheets there. These are assignment sheets. Okay, so classes haven't begun. No lectures are happening. I go and I find that there's a whole lot of questions which I have to solve within a week and meet the tutor. And I hadn't done my first year in Oxford, so I had no clue about how things were done there. I had done my 3-year undergrad. And so I had to catch up with not only what they had done, plus hit the library, read something totally new. And then I think I made some headway in a couple of questions, and I went for the tutorial. And there were some 3 or 4 other students, and I found I'd done more than any of them. After that, I relaxed. So it was I had a fantastic experience there. I think that confidence that people talk about, Chandru talked about how, and Ajit, that MTTS really helped them build their confidence. For me, I think having to sink or swim in Oxford really made my confidence go up a great deal. And the idea that I could, hit the library, pull out books, read the books, and make sense of the maths on my own was very, very enabling. So I'll stop with that. And I think, once I fell in love with maths, I've not fallen out of love as yet. So it still continues.
Thank you so much, Professor. We would now invite Professor Tulsi Srinivasan. She is currently a faculty member at Azim Premji University. Professor Srinivasan has a bachelor's degree from St. Joseph's College, Bangalore, and a master's degree from IIT Madras. Her PhD is from the University of Florida. Prior to joining Azim Premji University, she spent a year as a postdoctoral fellow at Ben Gurion University in Israel, and then worked for a few years at Ashoka University in Haryana. Her interests lie in topology, geometric group theory, and undergraduate education in mathematics. Tulsi ma'am, over to you.
Thank you so much for the introduction. Can everyone hear me?
Yes, ma'am.
Okay, thanks. So I want to thank the organizers for hosting this event and for giving me the chance to be on this panel. I've really enjoyed listening to my co-panelists till now. So I think in my case, I don't think I actively sought to find a career in mathematics. I think I just sort of went with the flow, like many people have already spoken, to see where the next step would take me. And the initial love for mathematics came through my exposure in school. And I think I didn't really value that enough at that time, because it seemed to me the only way of doing mathematics. So it wasn't very structured. We didn't have exams until I was quite, I was in the 9th standard, I think. There was a lot of aspect of exploration and play. A lot of my learning was completely self-paced. We would be given material, told to think about it, read about it. There were even years when we would work on the material and then get the chance to take the test whenever we were ready to take the test, assess ourselves, and then decide if we had learned the material or not. And that approach, I think, worked very well for me. So I think I now realize that I'm quite a slow learner. It gave me the chance to just take my time, immerse myself. I think also maybe I have some streak of independence. So not having to follow anyone else's timeline or rules, do as I wanted. That helped me a lot. And I think it suited the subject as well, because I feel maths is a subject where you don't have to rely on anyone as a source of authority. When you get it, you've got it. So you can keep going until you've got it. And this kind of an approach which is more centered around play and exploration rather than memorizing certain rules, I think suits the subject very well as well. And I'm afraid that's something that some people do lose out on during the course of their education. So I think this experience, I especially got interested in geometry. The relations between mathematics and art, I kind of felt maybe geometry or topology was something I wanted to study. And I didn't at that point think of a career in mathematics, but just that this is what I wanted to study next. Unfortunately, I think when I went for higher studies in mathematics, the more mainstream approach did not suit me so well. So I felt a little constricted by it. And I think like many others, I fell into the trap of, having exams to prepare for and trying to get through my courses, and didn't get the same pleasure I should have got from the subject. Again, I think I was a little lucky in that there were several, I was never an MTTS student, but I did apply through the IS summer programs and JNCSR, and I had a lot of mentors along the way who helped me, including actually Geetha, who is here today, who gave me some advice on what I should be doing for a master's. And when I kind of got through a few years like this. And I think when I started my PhD program, again, I found that love for mathematics, which had been missing for a few years. And I'm afraid this is a problem with the education system for quite a few people, that you see the play aspect of mathematics, the exploration, open-ended, fun aspect of mathematics as a child, and maybe you see it again as a PhD student. And for a few years, for many of us, it is missing. Perhaps some people do get the chance to see it. Maybe MTTS is a good opportunity to do that. So as a PhD student, I found it again. And at that point, I think another thing that really interested me was the process by which we teach and learn. Like many people who got interested in education, I was reflecting on my own educational journey, what helped me to understand the atmosphere in which one has to be in order to be able to learn, and the atmosphere in which one has to be so that you feel comfortable, you feel like you can open up when you have doubts, that you have people to collaborate with, that you get a sense of excitement when you learn something, you have the time to understand it. And when I started thinking about these things, and also about the many people, I'm sure we have all met people of that sort who were put off by mathematics because they never saw that aspect of mathematics. So I think that prompted me to want to teach. And so after that, looking for a career where I could teach mathematics, I was especially interested in teaching at the undergraduate level because, well, partly I'm scared of children, so I didn't want to teach at a school, but partly that's the time when I think mathematics also gets interesting. There's a jump from high school to college. And I think we do lose a lot of good students at that stage because maybe the way in which learning is done is not to their taste. So I got interested in teaching that particular student body, which is what I'm doing now. So when the organizers sent across the plan for this discussion, the other thing that I was thinking about was when they said what led you to do mathematics. I've been talking a lot about what I wanted and the things that interest me, and that played a major role. But I was also reflecting about the good fortune I had in being able to do this, and thinking about other friends who are studying mathematics. I think one is that I did not face any financial pressure. So this thing that you can do what you want and explore and find out what you want to do is a luxury available for very few people. For many people, there are realities related to finding a job and finding a job quickly, supporting your family and so on. I was fortunate not to face those. The other, especially as a woman mathematics student, I did not, again, face pressures from my family about getting married or starting a family soon. I saw so many students who were far more talented than me having to leave academia. If at all they had a job, it was maybe teaching at the place closest to where their family was staying. If they wanted to engage in higher studies, where they went was completely determined by where the family was living. I think these are pressures that a lot of people face. And again, I was lucky I didn't face them. And thirdly, again, some kind of peer pressure or family pressure about having maybe a glamorous career or a well-paying career. I think these kinds of pressures also, that if you do this, you are guaranteed a well-paying job, can take people away from something that they really love towards something that they might like or maybe aren't crazy about, but feel is the thing they should be doing. Again, that the absence of such a pressure gave me the space to really think about what I enjoyed and what I wanted to do. So I think that's all I wanted to say at the moment. But maybe we can return if someone has questions later. Thank you.
Thank you so much, Professor Tulsi Srinivasan. Now, moving on to the question and answer segment. It is both a blessing and a curse that our generation has excessive information available, and that is making students clueless. Is there any way in a regular curriculum that will help students sift through this information? Can you provide some tips to filter the plethora of information available? And also please touch upon the fact that students might be running towards trendy job profiles rather than actually exploring them.
Yeah, should I start or somebody else will start?
Sure, sir, you can start.
Okay, right. See, you're saying about the information availability. There are plenty of information available, but if you restrict the information availability to mathematics or mathematics education or getting a job after mathematics education, mathematics career, mathematics degree, I don't think you have enough information about the information. The availability of information is less, but still what happens is the students' attitude or anyone's attitude of easy going through, easy to do things easily. They go and search for information, they start believing it. So the best possible thing is when somebody has chosen mathematics as their career, okay, or if somebody wants to choose mathematics as a career, they should be aware of what mathematics can do. For example, there are various things which we come to know only after you do your PhD or you listen to somebody who talks about applications of mathematics, etc. Whereas if for other subjects, if they say physics or engineering, they say so many applications, application here, there, and all they talk about. When you talk about mathematics, I don't think even an average college teacher or university professor can come up and say something which a common man can understand. Those people who can give some lecture about how mathematics can be applied to some random crowd of people, it's very rare to find out. It's not easy. Okay. So somehow mathematics is not attractive for somebody who to choose mathematics. And most of them choose because they have to choose some subject they choose. Okay. Even if somebody is good in mathematics, like Professor Krishna Hanumanthu said, in school days itself, when those who score or those who do good at numbers, they'll be always called in Tamil Nadu Kanakupuli. Then they will be like, it's kind of, they'll be motivated to do. You do very good mathematics, do it. And then they somehow kind of has a tendency to go to mathematics course, and then they come, and even after they come to mathematics, they will do very well in their course and all, but then no teacher would be there to, very unlikely that there is a teacher to say that there are applications, you can do this and that, other than, for example, if they want to talk about a job, they can't say something. So the information with respect to mathematics education and after get a mathematics degree, how to get a job and all, the information is very less. Yeah. Am I audible?
Yes, sir. You are audible.
Somebody's mic came on.
Okay. So that's the first point. The second thing which I want to say is anything to do with reducing or taking what we want from a bunch of information, you need a common sense. And if you want common sense to be taught, I think the thing is you have to teach foundation course for those who come to mathematics students at a very early stage. For example, that's the only course. Usually when I studied, or even now, the UGC course, 2015 syllabus, it talks about several courses, and there it has some course called trigonometry, some course called theory of equations. These courses, it is like kind of from school you come, let us ignore calculus. I'm just saying calculus also the similar thing. There are easy courses for somebody who is interested or who has done mathematics well in 12th standard, because you are going to do some repeatedly the same kind of tricks to solve all the problems in that course. but then it doesn't teach you any abstraction. When you introduce foundations, the way we do in MTTS foundation course, this, you are giving them something very simple. That is, there are only two things you are going to say them, the meaning of them. Only the quantifiers, their existence for all. With that, we give many things with real life thing, and then just to teach them what is logic. We do sets, functions, everything with that. And then that is, in a way, it is easy. And it is also the course where you get abstraction along with. For example, trigonometry and theory of equation, it is also easy. Calculus, all of them. To solve problems, it is easy. But then it doesn't teach you abstraction. Abstraction is the core of mathematics. To get into abstractions, you need foundations. So the foundation has to be given at the earlier. But what advantage does it have to do with your common sense? What it does is, it will give you the habit of analyzing things. It will give you the habit of thinking logically and choosing what is right for you. So I would say that the course on foundation will help students to filter out what they want, what they don't want, which they can believe, which they should not believe. All these can be, I think that's what I feel. So thank you all.
Shall I say something? Is that okay?
Sure, ma'am.
Yeah. So I would like to add to what Chandru said. Basically, at the university where I am, we were very lucky because it's a new university. We started only in 2008, and we got the chance to design our undergraduate maths curriculum. And one of the things that I really wanted, because I was setting up things there, is this idea that in school, students tend to, have learned methods. And over the years, what I saw was that they hadn't even learned a method. They learned how to solve a particular problem. It had become that bad over the years. So we really, so when you get undergrad students in college, they come with this whole approach of having scored well, maybe in the board exam, and for which they ask you, there'll be peculiar questions like, what are the steps that you have to write? They don't know how to write. Very few of them know how to think about maths or even read maths. So what we wanted to do, and Amber Habib, who's I think also part, has, I think the MTTS people will know him. He and some others, I'm grateful to have these people around. We were designing the undergraduate program at our maths honors in our university, and we had a course, we created a course called Introduction to Mathematical Thinking. So the whole idea was to have a very gentle start to abstraction, but really get the students to enjoy proofs, proving, understanding, reading maths, thinking about maths, and writing and communicating mathematics via, so we had a bit of discrete maths, we had some linear algebra, some analysis. So it was generally you don't find that kind of a course typically in a UGC syllabus or something like that, because the whole notion is that at by the time you finish undergrad, you should know this much maths. And so it's all about, having many papers in which you do that. So I think that really helps students to even figure out whether this is the kind of subject they want to study further. So this is something that they did in the very first semester. And in our university, we have the option of students leaving one major and moving to others. So it also settled people, they kind of knew. So I think in the regular curriculum, it is possible to introduce a course like this right at the beginning, which allows students to really figure out whether they enjoy the kind of mathematics that they are going to study further as well. Because a lot of young people come into mathematics without really knowing that maybe they liked mathematics in school, but liking mathematics in school need not necessarily mean they like the kind of mathematics that they were going to study in undergrad. So this is one thing that I think can be easily done. There were some things sent to us on email also on the queries, and one of the issues was that students tend to want to do things like data science or other career oriented undergraduate courses. See, my own take on this is that you really need to study a discipline well. You study it well. I'm not saying you need to have a very you study it very widely, but if you study it with depth, then you will learn how to think. So I think the most important thing at the undergrad level is, being able to analyze, think, and every discipline does it in its own way, but maths does it wonderfully. I mean, you learn to you become problem solvers as well, right? And so I think it's better to actually do an undergraduate degree in mathematics rather than something in data science or related things like that. You should, if you do your first undergrad degree well in a discipline, I think you'll be well equipped to take up almost anything you want. But I think that's a kind of question that's going to come up a little later. So it's definitely possible to design within regular curriculum things which would allow students to enjoy and understand what their maths is about. It also has to do with how you approach the teaching. Students also think that maths is kind of given to them, and they forget that there's a long history before you came to, say, the kind of abstraction that we do now. So it's very important, I think, also that students get to know about about the history, and not in I mean, there are terrible history of science courses. I would not recommend that for anybody. But I like, before I start any topic, teaching any topic, I like finding out how things originated there, and I like communicating that with students. And there's a wonderful site, History of Maths, in St. Andrews, University of St. Andrews hosts this. If you just type Math Tutor into your this thing, you'll find a huge amount, and I think that's extremely important as well. So I think teachers, MTTS types of program, having good mentors, having syllabi which are meaningful, which allow students to make a sense of what they're getting into is very important. And I think it can be done. That's my sense.
Tulsi ma'am, we would now like to request you to share about this. Also, we would like you to touch upon the fact that a lot of information is available to the students, and they are just gathering it from anywhere. But is that information reliable, and are they actually making good use of it?
Thanks, Anthony. So I think I first want to say that I completely agreed with what Geetha was saying about the value in the mathematics degree lying a lot in the general skills you pick up on how to read mathematics, how to write mathematics, how to reason, how to just spend a lot of time with something that is difficult and try to get over it. The discussions you have with friends, brainstorming when you're stuck. I think these are the skills that are really the transferable ones. So I think one thing that I want to say right at the beginning is about the information will come and go. Today, this career is being touted as the biggest thing out there, and tomorrow something else will come. And neither should we as the designers of curricula plan around that, nor should students plan around that, because I mean, we should also be aware that there is a limited number of jobs out there. In the economy that we are in, PhD students are fighting over a clerkship. So for our students to say that, I will do an online course in Python and that will make me employable, it's misinformation being fed to them from all directions. I'm not even sure what the source would be. I think if someone can shed light on that, maybe it's friends, maybe it's family, maybe it's ads on YouTube telling you, now on my road, the road that I go to work, there are ads saying that X is a delivery person for this company and X is going to become a software engineer or something by taking this course. So this information is everywhere that you need these somewhat superficial seeming skills, which will take you from here to here. I believe that is not true in terms of the skills, and I believe it's also not true in terms of the availability of jobs. So I think maybe, I know it's not very realistic advice for someone who is facing pressure that they need to graduate and find a job. I'm sorry, I can't be more optimistic about it. It's a bleak situation. There are not so many jobs out there, but maybe the best thing for students to be doing is to then focus on learning something well, even if the pressure is coming from outside that, get the superficial skill, add on to your CV. Whatever advice is being given to one person is being given to a lot of people. At the end of the day, I believe all those CVs will look the same. So it's much easier for me to say than for students to do, but if perhaps the culture in students' classes can change, where people get together, put aside the pressures, and try and really immerse themselves into learning something well, I believe that might be as fruitful, if not more fruitful, than reacting to particular pressures. Sorry, I believe for a student that will not be useful information, but yeah, I think this is the advice I would give my own students.
Thank you, ma'am. Krishna, sir, we would now like you to say something about this.
Yeah, so I think the previous panelists have said mostly what I could think of, and I agree with everything they said. So I just want to maybe add or enhance some of this stuff. I interact with undergraduate students at CMI. These are not too many, but I think I get a sense of what our current students think, not just CMI, but in general, current generation. I find that there is a fundamental difference in, this is like an old person speaking maybe, but I find that difference between 25 years ago to now is there is a certain utilitarianism in everything currently students do. If I do this, what will the use for me be? I don't think we thought like this. And I think thinking like this is very dangerous, because of course you think like this when you choose a direction. You want to do BSc or MBBS or engineering. Of course, there you have to think what you want to do. But once you choose something, which course you want to take or which lecture you go to, this is a trend I see. It's unfortunately not just sort of isolated, but I've seen this across large number of students. And I think the issue of having too much information available is particularly dangerous here, because they think that I would like this course, or like as was mentioned, I want to learn Python, or I want to learn some other particular skill which I can pick up in a course. But if that is all you're going to do, and I don't think a student obtains a level of mastery or expertise in any subject like this. So there are some fundamental sciences. One has to learn them well and then add on to them as you go along based on what you actually want to do. So I think mathematics, if you want to do, it has to be, whether you realize that this is useful or not in future. Sometimes it may not be useful, to be frank. All the courses that you're doing, all the theorems that are being proved in class, you may never see them in life again, or you may never use them. I think that is for sure. I see it's easy for us to understand that over a 3-year period coursework, you do a lot of things that you pick up a few things, you remember them, you use them. But I think what you should think of is in the following terms. Each thing you're doing is making you better at something. So it's like you're training your brain to function in a certain way. Like if you think of musicians, for example, this is something we all I think understand culturally. Musicians practice a lot. Even very senior musicians, when they perform, right? They just sing or play whatever the instrument for hours and hours. I used to wonder why do they do this? They're obviously very good at this particular item. They know very well, but why do they keep singing it? And the answer is that you have to stay in that you have to keep practicing to continue to be good at this. So I think mathematics is something like this. You do problems. For example, I tell my students that when you do mathematics, we use the word do mathematics. I mean, this is a very instructive word. We don't study mathematics. I mean, we also say we study mathematics, but in our day-to-day language, we say do mathematics. So you do problems, you do exercises. So this is very important. And each exercise, makes a small connection in your brain, which you may not realize, but it's one additional thing you learn, which may come in handy later on. So I think you have to study because you like studying it, because you think that all this learning will be useful in some sense. But you can't say that this is useful in this concrete way. And if so, I will do it. Otherwise, I will not do it. I think this is not a good attitude. So, this generation has, it's like a very good resource for them, all this information. And I think if used positively, it can really help a lot of people, because you want to listen to somebody's lecture, which will help you a lot in understanding the material, or you want to find exercises that are actually interesting and will help you. So earlier we used to just look at a book and that's all. And maybe the library had 10 books on it and we only had access to those. Now you have many more options, but I think the flip side of that coin is you can be too distracted. You may not be able to focus on something. So it's very good to keep a small set of things you want to do. I think this tendency to want to do too many things is very common nowadays. So you should not want to do too many things. Pick the 4 or 5 courses you're taking in that year, that semester. Just learn them thoroughly. Anything else you can postpone. So I think students should think like this. It's not sort of how many things you know, but how well you know what you know that's more important. So I think students should focus on getting rid of this, very utilitarian attitude to learning mathematics and just do hard work. I mean, this is just very typical, standard thing people say for hundreds of years, but I think this is still true. You just have to work hard and not worry about what benefit you're getting in the immediate future. So that is, and I think if you have that attitude, generally things will work out. You will know which resources to focus on, which resources you should not focus on. Okay, yeah, thanks.
Thank you so much, Professor Hanumanthu. Professor Ajit Kumar, we would now request you to give some concluding remarks on this topic.
Okay, so I think already people have said, and I quite agree with all these things. So I will just also kind of stress upon this. I think we are talking about the mathematics students. So I think they do mathematics because it's beautiful, right? All of us love doing this mathematics. And I'm sure, I think this audience knows that the usage of mathematics in our daily life. I mean, even if you look at the society, it says that if you can do mathematics, you can do anything. That's the general belief. And I think most of us, when we choose this mathematics as a subject, I don't think we bothered about what lies in the future. That was, I don't think, was the kind of thing we had in mind. So my advice is that do mathematics if you are passionate about it. And for that matter, any subject, if you are passionate, if you love doing, do it. And if you have mathematical skills, I think job will follow you. But the mathematical skills is what is important. And I believe that all the syllabus, if you look at any syllabus in the country, undergraduate or postgraduate syllabus, most of them are quite, I think, good syllabus. There is no problem about the syllabus, but they should learn the concept well. And if you look at, of course, whatever, I mean, this is quite idealistic what I'm talking about, but then that is not how majority of the student think. And that is why they are having this panel discussion. And at present, you have lots of information available. And in fact, I think this is best time for student to do mathematics. We are at such a juncture where most of the things that we learn at undergraduate and postgraduate mathematics are useful in some way. I mean, earlier, if you look at some, let us say, 25, 30 years back, when we call that as maybe, let us say, industrial age, where only certain skills in mathematics were kind of, if you have that, you get the job. Whereas now we are in the age of this information technology, where developing algorithms, softwares, etc., is becoming very important. And what you need there, you need kind of logical thinking to solve any problem. And that is what students in mathematics learn. So if they learn this mathematics properly, I'm sure they can make a career. Of course, in academic or even other places. As far as this lot of information is concerned, as I said, first of all, whatever they are learning, they should learn it thoroughly. There should not be any compromise on that. But then there are so many other things which are available. These online courses, etc., possibly can be used as a supplement, not as a kind of alternative to kind of classroom teaching. And I'm actually all these MOOC courses, NPTEL courses, and all these things, which a lot of things are there. I think there are certain studies that these are not that effective. In fact, I have also given a couple of courses for the last 2 years it has been running. And what I find is kind of, even for my course, almost close to 2,000 students had registered. But when it, I think most of them possibly would have just listened to the courses. But when it comes to submitting the assignment, solving actually problems, and taking the exam, the number is very, very actually less. So, I mean, I think these resources, they can use it to supplement what the skills that they possibly require in getting job. But another thing I would like to say is that at this stage, of course, the students have a lot of information, possibly they are confused, etc. That is where the teacher's role is also very important. I think at this stage, as a teacher, we should also be aware of what are some of the kind of relevant information that student can possibly look into it. So, in fact, if you look at this is about the software technology. Bill Gates once he had said the technology is just a kind of tool in terms of getting the kids working together and motivating them. But the teacher is most important even in using these kind of tools. So I think we as a teacher also have to kind of get acquainted with these informations and suggest the students what is good and what is not kind of good for their career. So I think that's what I would say. Over to you. Thank you.
This plethora of information is somewhat like a mess, and what mess reminds me of is what world was and is dealing with right now is after effects of pandemic. So maybe Chandra sir, can you share your experience of online teaching and the transition, and what was a common and average student's mindset during the classroom, observations you made? Maybe we can start off by that.
Yeah, thank you. See, I taught for about almost 4 semesters online, and the general attitude for the students is it is easy to go through the classes. They can mute. See, the students from my university come from, most of them come from rural background, at least half of the students. And they say they don't have internet connectivity, they don't have proper device. They even say that they don't have good mobile or something. So it's very difficult to force them to switch on the camera and all. And they'll come, they'll keep muted, and we don't know whether they are there or not. And in fact, we have to depend on 1 or 2 students who will respond out of the class. So the students who really want to learn, very few of them, they somehow they learn. The other students, they just want to get through this, and they are enjoying. They're not bothered about this. There are few cases, very few cases, where there are actually genuine difficulty in taking the course. Otherwise, they have taken it as a kind of some students. I remember throughout this university, he had arrears in various departments. Around 16 exams he has failed, and then once just after this COVID, an online classes and online exams started, he cleared all the 16. So what do you expect? So does he become very bright and he become very studious sitting in his home? Or the teachers have become very efficient teaching in online? No, it's not. So teachers are not efficient. Students just want to skip through this. And many teachers are not tech savvy. Many teachers, almost 90% of the teachers, they are not comfortable using a computer to teach. I have seen they are struggling to set up, and there are very many different things. In fact, the first semester and second semester, many people are not aware about what tool they have to use appropriately, and especially for mathematics, it is much more difficult. Now you can't keep on. So those students, those teachers who are not comfortable in preparing beamer slides or something which will properly present the content, and for every day you have to create every lecture. That's not possible. So they need something to write and do. So some teachers, they came up with the easy solution that they'll put a camera near the board, some 3 or 4 feet away, and they'll start teaching. They record it and then post it. But then in that case, what happens? The board will not be clear because the camera which they had was not a good quality. All these are there. Even if the student have to watch, he can't do it. So he can't learn many things from that. So it's kind of drawbacks from both sides. Essentially, there was no learning happening. Only learning that could have happened is that could happen on the student's part. See, generally, the mathematics thing is, even if you have the very best teacher in your class, and if you are not going to do it on your own, if you are not going to try it on your own, you are not going to learn anything. So I don't think mathematics teaching, it's going to have a very different thing compared to what you teach in online class or what you teach in person. See, in person, only thing is the teacher has the benefit of identifying whether the student responds or he is listening or not. But that is not happening in an online class. So now what happens is, if a student has the habit of trying to learn on his own from whatever the teacher has taught, if he is trying to recollect or review or consolidate what has happened in the class, unless otherwise he does that, he is not going to learn just by watching. Even if he watches all the lecture without losing attention, and he is not going to learn anything. So the general thing I feel is, because of COVID, there are difficulties. So those students who might have, by looking at the face or just to impress the teacher, might have done some work, done some extra work and try to answer so that he'll be in the good books of the teacher. Some such students will be there, some proportion, who want to be with the good books of the teacher and other things. So those people will do because of the teacher. So such people might not have done, but otherwise, those who do on their own effort, they will learn, but otherwise they will not learn. So that's the situation which has done in COVID. But one thing, it has made students more lethargic about studying and other things in general, and that lethargy continues even after the COVID thing is over. So that's what I feel. So that's it. Thank you.
Thank you so much, sir. Krishna, sir, can you enumerate a few differences you felt like in post-online era and like classrooms you taught in supposedly 2017, 2018 era? So what is like a basic, maybe the differences you felt in students' behavior, their basic understanding, etc.?
Yeah, so I think, as Chandru said, there is almost nothing good about this online classes. I think, I don't know, I mean, I can't think of even one positive thing from it. So generally, certainly this is, I think nobody liked it. Students didn't like it. Teachers didn't like it. and my daughter was taking classes at home. She didn't like it. Her teachers didn't like it. So this is universal, I think. So of course, this is, for some people it is inconvenient. For some people it is just impossible. Most of the people that I taught were, they had devices, they had different rooms or some quieter places. I think this is itself a privilege that many people don't have. So for a large number of students, there was no question of online schooling at all. So that is, of course, tragic. But among students that I taught, generally students, I think, are more likely to work if they come to class and more likely to pay attention, because they can be doing other things, but it's very difficult to do too many other things in a classroom, right? Because they have to, you look at them, so they can't, for example, watch something on their phone so easily, at least. So they have to do sit in the back in some corner or something. So whereas in an online lecture, there is no way that we control what students are doing. And as Chandru said, we can't really tell them to switch on the video. For one thing, for many of them, it's a real issue. For another, really, I can't do much. I mean, I see 30 people in my, small window, and I don't know how to keep track of what they're doing. So essentially, they are doing whatever they want. And, I attended lectures also where I was doing other things. So it's not surprising that students will be doing other things. Now, this is very problematic in a course, because if they miss, let's say, 2 weeks of classes, or they don't pay attention, or they don't do enough work, then it's very difficult to get back to focusing on things. And a natural tendency is that they will just not pay attention. So this has become much more an issue during the online era. And as teachers, of course, we face this issue of giving exams. So this was a big problem. How to give an exam and be sure that this is genuine work. Most of the time it was not, right? Because you have no control on what they do. So I think, hopefully this is over, and we are very fortunate that, this is now we have gotten back to in-person classes. I think maybe one good, I don't know, all of us doing online things, we have become a little more comfortable with devices. So at least, in the beginning, I remember that somebody keeps the video on, somebody keeps the audio on, we have to keep telling them. And, we had no, so there are no commonly accepted behaviors and rules about this. I think now everybody knows. In my daughter's school, she was in 4th standard, and it was a mess. Like, everybody was doing whatever they want. But I think towards the end of lockdown, everybody knew how to behave. As soon as you log in, you switch off your audio. So I think people got used to this. I think people, my parents' generation, they also figured out how to get into this. So I think that is one good thing. People now know how to make use of this if needed. But as far as education is concerned, I think online does not work, in my opinion. Like Ajit said earlier, you can supplement sometimes with online courses and summer lectures, but it can never be the only thing you do. I don't think you can learn at an advanced level, like at a BSc level, I suppose, or at any level. Purely online, I think, is very difficult to learn. You need this face-to-face interaction. And more importantly, I think students need interactions among themselves. See, the problem that many of them faced was they were sitting at home and they were taking classes alone. They had no peer group to fall back on. So whereas now students come to, most of these institutes have hostels, but even otherwise you spend the whole day in the college or university and you talk to each other. I think that is very important. So I hope that period in our lives is over. And I think it's very unfortunate that 2 years were spent like this. And I don't know, this 2 years might have lasting impacts, and people may, I taught a course which, a student finished it, and technically that person knows this subject, right? If that person got a good grade, but I don't really know if actually they know. So hopefully this is not happening again, but I could not figure out any way of making this work. I think it was just something that we were forced on. It was forced on us, and somehow we managed, and I really hope that it's over. Yeah, thank you.
Thank you so much, sir. Ajit, sir, can you point out any solutions to the fact that many potential students who could do great in academia are like drifting away from the mainstream mathematics just because of lack of basic understanding or this gap maybe?
I mean, you said people having good at mathematics, but still they're drifting away from it. Is that what you meant?
I meant to say that there are students who have potential, but due to many reasons, yeah.
Yeah, right. So yeah, first of all, see, I mean, students have to kind of identify what they're good at, right? So once they identify what they're good at, then of course, in this information age, they can find some alternative, even in math courses. For example, somebody may be good at coding, and in fact, I am one of somebody who generally advocate that all math students should do coding. It brings a lot of advantages. And in fact, I advocate that even at early stage, students should start learning coding. So, and then they may not be very good at mathematics, but they can possibly find out usage of it in some software or other things, etc. So they can find their ways. Not everybody who are doing BSc mathematics or MSc mathematics would go and become mathematicians, right? But then they can definitely find some what do you say, alternative which will make their career in still usage of mathematics in various fields. So I'm not sure whether they are drifting away from it. That maybe is because of some other reasons, etc., but not because of the reason that they don't have a proper guidance. I think that's what I would think.
Thank you so much, sir. Geetha ma'am, can you point out a few corrective measures like today's student can take to overcome this gap or that pandemic has caused in our lives, like an educational gap?
Yeah. I mean, I agree with Chandru and Krishna on the trauma of online teaching and learning of mathematics during the pandemic period. In fact, I would like to. I recently taught a batch offline of undergrads who had, only seen online teaching since they entered college, and I taught them first course in algebra, and I found that whatever I expected them to know from the previous year, they basically knew nothing. So literally, while teaching them, I had to keep revising older parts or something even from school which they needed to know, or what they had, a little bit that done in their first year and so on. So I think one important thing, particularly when you're teaching batches which have learned online during the pandemic, is to maybe shore them up during your teaching. Also to point out to them that, look, if I'm teaching this particular topic, it relies on, this information or this basic stuff which you should have done earlier. And I think also to tell them that, look, if you're not very familiar with it, go back home, read it, study it, and so that whatever I've taught you today starts making more sense. right? So I think the one of the things in maths is this continuity. I mean, what you teach in a particular year usually builds on what they have done in a previous semester or semesters before. So I think as a teacher, it becomes very important to identify the fact that you know that they haven't learned much during this pandemic period. So you have to, it's not possible for you to teach the entire course again. So you have to make sure that they have material available. In fact, one of the interesting things that happened this year is that even though I was teaching offline, the students knew I had taught this course online previously. So they wanted all the lecture notes and the recordings from the previous year to be made available to them, which I did. Because at the end of the day, you know, whatever helps them to learn and to learn better, I'm happy to do that. The only worry I have is that, the only way to learn maths is to do maths. And there is no shortcut in it, right? I mean, so if I've provided a lecture which you sat in my class, listened to me lecturing on a particular topic, and after that, I would expect that the student has, written down, made notes of the discussion, which I'm not going to write on the board, noted things down. Instead, I do find that there is a tendency now to rely, okay, I'll go see the lecture, I'll stop it at that point and listen to the discussion again. That's all right, but at the same time, I think you need to internalize things when the class itself is happening. Be prepared for the class when you go for it. You do know what is going to come up in the class in the future. Have some sense of, what you should know previously to understand what's happening in the class. Because every time there's a discontinuity there, it's going to take exponentially more time to catch up. Now, I keep telling students, don't waste your classroom time. If your teacher's there, you can ask your doubts, you can clear it on the spot, you can come back the very next class and ask your doubts. But if you let it lie for some time, then it becomes very difficult. So I think one of the things is, as teachers, we have to help the students overcome the gaps that they definitely have because they've tried to learn, or actually they haven't tried to learn online. They tried to pass the exams. That's all most of them did. Okay, so that's one thing. Second is, yes, I mean, I'm happy to provide lecture notes and lectures, but I feel a bit reluctant at the same time, because then I wonder if it prevents the student from doing that little bit of hard work which is required for doing any mathematics. So, I mean, so I'm caught between wanting to readily provide things and then wondering whether I've done the right thing. So I think that maybe the students need to tell me whether how really these things are helping them. Apart from that, I think the fact that they are in a classroom and they have that social interaction, peer interaction, that makes a big difference. And one of the things I think people should remember is most undergrads, even those who are doing mathematics, will not continue with mathematics. So your undergraduate life is also about experiencing everything that undergrad life has. That's the time when you're making, your life as an adult is starting around that time. So there's a lot of things happening with students. You have to learn balance. And maths does demand. So if you want to do maths well, you have to learn to manage your time very well. But that should not prevent you from doing other things. You should be experiencing a lot of things during your undergraduate period, but you cannot neglect your study of mathematics, because that is what is doing that well is what will open doors to you. And I think what I agree with what Ajit says. I do think that programming is something that students should learn very early on. And you can integrate it with all mathematics in that sense. So having labs, because it also gives them a way of trying to see the patterns and sort of see how the maths is working by themselves. And I think that's really important. And we do have a lot of technology now which can help in doing that kind of exploration. So I think these are the few suggestions I would have for, but at the bottom of it all is the student has to do it. They have to be willing to put in the time and effort, and they have to do it by managing their time really well, so that they can experience all that undergrad life has to offer, but not neglect. Sometimes they do everything else that undergrad life has to offer and not the program to which they have signed up to study. So that shouldn't happen. Thanks.
Thank you so much, ma'am. Now maybe Tulsi ma'am, can you conclude this topic by giving your insights on the same?
Yes, sure. So, yeah, I think I agree with many of the points that all the panelists have brought up. I think one aspect that really stands out for me from what has been discussed is the social aspect of doing mathematics. And in some sense, I think the pandemic also reminded many of us as teachers of how important it is, because I don't think we can, if we look back on our own education or the universities around us, we can say that before the pandemic, colleges were doing justice to the social aspect of mathematics. Perhaps the pandemic was also a wake-up call to us to remind us that if you stand at a board and lecture for 1 hour, no one is doing mathematics in your classroom, not even you, certainly not the students. So I think, yes, there are tools that many of us picked up during the pandemic, which perhaps we can incorporate into our classrooms. But I think what communicates what mathematics is to students, so they get the taste of doing it, the taste of discovering it, discussing it, being wrong, making mistakes. There was perhaps even in the normal course of affairs, there isn't much opportunity for it. But during the pandemic, there was absolutely no scope for any of that. So having, all of us having gone through it, our students having paid the price for those decisions taken by universities, perhaps at least one thing we can do is now try and correct for that as we plan our courses further. Maybe these, I think classes with 70, 80, 100 students, perhaps these things cannot be done there, and we need to start thinking about whether classes should be made smaller. Maybe even, I think Geetha's incredibly important point that most of our students at the undergraduate level will not be doing mathematics later. So then what are they going to be doing? What can they get out of the classroom? Perhaps we can think about ways in which they can get some skill out of the mathematics they learn, even if they don't, for the rest of their lives, remember what is an abelian group. They get the experience of having understood the definition, perhaps more active learning, more group discussions, more explorations, presentations, reading popular articles. Maybe we should be revisiting what our classrooms are like after the experiences we've had in the last few years, and seeing specifically what was missing for students during that experience. Yeah, I think that's all I have to say on this. So, thanks.
Can I just add something? Hello?
Yes, sir, sure.
So, of course, all of us know this pandemic was really bad, and it has really hampered the teaching and learning process. But there are, it has also given a lot of opportunities. So I also look at this as providing opportunity. We have learned a lot of skills. Many students, in fact, they have used this and in a way that they learned what they wanted to. For example, one of my own student who was actually from UP, some remote place, and he got into the PhD program in Harvard. And he said that, sir, I could manage many things, etc. I could do projects of my choice. because of this online thing, I could manage. So, and for example, look at Professor Kumaresan, how many videos, lectures he has created, and in all the subjects. And I don't think, but for pandemic, he would have done this. And for example, you people are doing great job organizing all these things, etc. I think it's possible because you could do it online. And like that, so there are some positives also. It has given us a lot of opportunities. So not everything is very, very bad. Of course, those who wanted to learn and wanted to teach properly, it definitely, I mean, I don't think it was complete washout as I don't think that was the case. Right. So, I mean, I just wanted to kind of say. Thank you very much.
Thank you so much, sir. Does any other panelist have anything to add? Or if not, then we can move on to the next section, which would be done by Priya.
So like, I believe during this pandemic session, pandemic period, there were like thousands of online courses. Like, for example, this data science, machine learning, Python, programming and all. And students were blindly going behind them. And some of the students may want to get placed and they believe like this mathematics with data science, machine learning together will be a great combo pack for their placements and all. And many of the students don't know whether that is needed for them. And they are doing this mathematics as a BSc course, and they are also learning this other kind of online courses. So they are actually confused and maybe they are not getting actual information. So in the academic curriculum, so what do we need like interdisciplinary courses in the academic curriculum? Because some courses is actually necessary, like this programming, Python, coding, that actually helpful for the mathematics students. So how can we modify this academic curriculum so that we can include some interdisciplinary courses, which is actually helpful for them? So Ajit sir, can you give some insights?
Yeah, I think in this present age, we do require some of these supplement courses. However, in this, if you look at this so-called machine learning, artificial intelligence, etc., and data science, basically, so in the core of all these things is linear algebra. Right. So if the student learn linear algebra very well, it will be really useful, because you talk about any data, it's basically matrix, right? So if I want to analyze any data, I have to learn matrix computations, right? So this linear algebra is the core of all these things, which I think all the BSc courses definitely have not one, but at least two courses. But what we require is in the course itself, maybe introduce little bit of applications. There are lots of books these days which talk about the applications. So in fact, generally, when I start my linear algebra course, for first two lectures, I just give them a lot of applications, including Google search and other things, etc., image processing. And then I motivate them that these are all these things, what you see here, we are going to do it in great detail in linear algebra. We will prove all these things, etc. So one can supplement similarly in calculus, but I think even for general these mathematics courses also, maybe a little bit of probability and statistics in this current data-driven information is very important. Of course, it could be supplement, or because if it is an undergraduate mathematics course, I'm not sure whether they can afford to have a statistics course separately, but student can learn with a little bit help. So I do think that this is important. And as I said, along with all these things, computer programming is key. That is essential if they want to have career in this kind of thing. Which programming language they learn, that is immaterial. Any programming language, if they learn properly, it will be useful, right? So in fact, that is what we at ICT, we have a course on called MS in Engineering Mathematics. That's basically as a name, but what we focus on basic mathematics. And then apart from that, we have some three courses in statistics, basically applied statistics, couple of courses in programming, and of course, they do other numerical mathematics and all these things, etc. And I think most of the students do get placement. And in fact, so much so that many times the several of these companies are coming and saying that your course is really kind of useful for whatever we are wanting, but we don't have enough students. So, but actually we keep telling them, whatever you do, first basic fundamentals, whatever you are learning, that has to be learned properly. Whether it's linear algebra, there's even group theory or calculus analysis, all these things have to be learned properly. Okay, so this little bit of extra supplement on this applications, little bit of programming, probability, statistics. I think these days, if they have, as I said earlier, if they learn these things thoroughly, there is no dearth of job as such. And one more thing I would like to say, see, in this very vast or fast changing, technology age, it is very important to kind of be able to adapt to these changing needs. And unless they have they are fundamentally strong, they will not be able to do. If they just are user of this technology, tomorrow they will find it difficult. So that is where this strong foundations on all these things is going to be essential if they want to survive, even if they go in this industry. Okay. Yeah.
Thank you, sir. Tulsi, ma'am, can you add upon this?
Yes, sure. So I think the points that were made before about the kinds of ways in which the typical undergraduate degree in mathematics can expand a little more, I would completely agree with. I think especially, at least when I was studying probability statistics, areas like that were not given so much importance. Programming was not a standard part of the undergraduate curriculum. I think at least programming, at least when I look at colleges in Bangalore, that's changing. Most students do learn some programming language. But I think I have a slightly different point to make as well. In addition to this, I think when we think about university degree being interdisciplinary or multidisciplinary, we should not, again, conflate that with providing skills for particular sources of employment. And again, I like what Ajit sir said about our students should not become users of this technology. The idea behind having a university degree or a college degree or BSc, as opposed to some vocational training or technical training in one thing, is that you think beyond what you receive in the classroom. So to me, what would be an ideal interdisciplinary mathematics degree would be for the student to take a course in philosophy, take a course in political science. That way, if they end up, working as a data scientist, working with algorithms, working in the financial sector, they understand the social context in which all of this is happening. So they don't blindly join a social media company and start developing algorithms for them without thinking about the impact it's having, without thinking about the ethics of what they're doing. They don't become consumers of such things. They don't give their data away. They don't get involved in some sort of slightly shady financial setup, but they are constantly aware of the world that they live in, and they use their mathematics not only in algebra or analysis, but they use their foundations in mathematics to understand the foundations behind these things and perhaps even question them or so yeah, for me, when the NEP imagines a more multidisciplinary, interdisciplinary approach to a degree in the arts and sciences, this is what it means to me. Not that a mathematics student does a course in data science or does a course in algorithms, but that a mathematics student takes a course in economics, takes a course in sociology, and really understands the context in which science is created, understands the context in which mathematics is created, the context in which they are used, the context in which they are misused. I've been talking about misuses, but maybe I just very briefly talk about the uses as well. I mean, during the pandemic, there were many scientists and mathematicians who were putting whatever skills they had to try and understand the maybe the spread of the pandemic, the economic impacts of it, all kinds of things. And there were also a lot of mathematically unsound models being put out there. And again, a student of mathematics should have not only the mathematical skills needed to produce such things or critique such things, but also the general social understanding to do that. So to me, that's what interdisciplinary or multidisciplinary means, to have your subject, but to not forget that there's a world in which you are practicing that subject. Thank you.
Thank you, ma'am. Now, Krishna sir. Sir, can you please tell about the interdisciplinary courses? I believe in CMI there are some interdisciplinary courses.
Yeah, so I think I really don't have many things to say, but agree with both the panelists who spoke earlier. So, yeah, so there are two aspects, right? It's interdisciplinary in the sense of, improving your job prospects and, preparing yourself for the current market, demands, which I think, the interdisciplinary courses related to for a mathematics students, if they do computer programming or some data science related things, that's what it would be. But I also think interdisciplinary should be viewed in that larger context, as Tulsi talked about. So yeah, so it's not I don't know what more I can say. CMI is a very small place. We do have few opportunities, some very small number. So we do have, of course, data science program, but we also have a humanities program, which is very small, but students are given the opportunity to take some 1 or 2 courses during their BSc where they learn. We use artists or people that we know in Chennai especially, who come and talk. So I think it's very important. This is something we are addressing. This is not maybe so much the issue in other larger colleges and universities. There's already a existing setup in those universities for an interested student to pursue other areas and other subjects. In CMI, we are slowly, doing that on a small scale. But I think it's important for an undergraduate student to have a well-rounded education. They learn something in great depth, but they should also learn more about the world and not just in their particular area. So I think this is more to do with the opportunities available in the place you study and try to make the best use of them. So I don't know more. Yeah, so I don't have too many more things to add to this. Yeah, thank you.
Thank you, sir. Now, Geetha ma'am and Chandru ma'am, if you have any points, you can add.
I can say something. Can I start?
Sure, sir.
Go ahead, Chandru.
Yeah, okay. See, generally this is about the interdisciplinary thing, but the idea behind that interdisciplinary course is employability. So, see, my opinion is, in general, if somebody understands and studies mathematics, they are trained to do critical thinking. They'll be a better decision makers. All these luxuries will be there. And what happens is, in at least in our scenario, in Indian scenario, most people who are good in mathematics in the sense of their thinking and doing research and other things, they somehow got sucked into academics. Most of them. They are not very much willing to go outside academics and do something in the industry. And very rarely people go. Some people from ISI, they are going outside academics, even after doing good mathematics. But I have seen many of at least my batchmates, my juniors, my seniors, those who are good in mathematics, they are getting into academics. So that's the first thing. So now the interdisciplinary course, let me come to that. So if I want to design interdisciplinary course, I can't suddenly remove some course from my MSc or BSc course and add some additional courses which they learn some other subject. That's not possible. As Ajit sir said, we need linear algebra, some amount of all the basic courses we require. Without that, we can't do anything. So now I will say first the general drawback in designing interdisciplinary course at colleges and universities in this country. Leave out NITs, IITs, ISERs, CMI, TFR, CBS, all these kind of institutes. And in which, if you see, not even 0.5% or 0.05, maybe 0.1% of students of mathematics will be studying there. Okay, ignore those. So they are not going to, we are not going to worry about the majority, are the almost everywhere. Okay, that's where we are going to look at. So there you see the whole curriculum was somehow influenced by UGC. Influence has listed something like list of courses and their nomenclature for names of the courses. In which if I am going to do the interdisciplinary courses, it should come one of this list. That name of the course should come in one of that. Okay. But then even if we get some special permission or do something and somehow autonomy or something is available with universities, but colleges cannot do, autonomous bodies, they can do. They start a course, then those students will have a drawback of not able to appear for standard jobs in the government or standard appear in standard exams in CSIR, GATE, all these things, because their eligibility will not have this course. And then now UGC has allowed online courses, okay, to be credited in their coursework. So that means in the certificate, it will also be, and suppose he obtains obtains a certificate from NPTL or some other place, and up to 20% of his courses can be from online. Okay, that actually I feel that is a drawback. The reason is, see, not I would say that in some sense among all the courses, this initially MTTS courses, okay, online courses were done with utmost care, and the amount of effort needed for doing that or doing successfully is too much compared to any teacher who is going to do it for them, for themselves, for their own courses. Okay, so it's a team effort and a lot of thinking went into it, and that success is, we can't repeat it in every classroom. So this allowing online courses, that's going to be a drawback for introducing multiple interdisciplinary courses, because online courses otherwise it is not effective, because we don't put in that much effort to make it more effective. And there is another drawback is academic bank of credits introduced by UGC. That means if I study first semester in Central University of Tamil Nadu, then they will allow me to continue with whatever I have studied the same program somewhere in Central University of Kerala or Karnataka. That means both of them should have, in some sense, the same set of courses in their MSc or BSc program. Okay, if they are going to implement it, see, many of the UGC guidelines have come, and some of them were not implemented, not successful, because they later realized that it was wrong. If they also realize that it could not be implemented and it goes well, it's good. But otherwise, we are in trouble. Okay, so these are the drawbacks. If you want to introduce, these are not drawbacks. I think I should say these are the obstacles if you want to introduce new courses, interdisciplinary courses. Okay. Okay, like ignore this. Suppose I want to do it, then what I need to do is, first thing is, we have to introduce in all math courses Python and Sage Math. The reason I would say with Python and Sage Math is the coding is very simple, and especially for students who has mathematics background, the code written in Python is also something very similar to how you write in mathematics. Okay, you write for x in p, we have x is equal to something, right? This is what a standard statement in mathematics, right? So the same line which will be written in mathematics in Python code, for x in something, something happens to x. That's what it will be written. So the understanding of Python will be easier. And Sage Math is something, it's like a collection of various open source tools that help us do lot of wonders without paying money. And that is written on Python, Julia, and other language, but it's easy to do. When you know Python, it is very easy to do. For example, I'll cite one reason. A chemistry professor had difficulty. He has done experiment for about 3 months, and he and his student, they have to plot this, and they could not fit a graph. It's not fitting to the model which they had, and they use a paid software called Origin or something, and there is a problem. So he came to me, can you do something? Then I said, I will try with SageMath. The same data I tried, and I learned what kind of regression tools available in SageMath. I did it. We may not believe it. It's just a 2-line code, and the fitting came very well. And in fact, I could manipulate the model in such a way that are there any other model by changing some variables there in the model so that we'll have a better fit. I can do that and all. So that way I say SageMath is very much important, not only for mathematics courses, physics, chemistry, and other people also. It has a lot of available tools. And then we should also do something as teachers of mathematics. What we should do is we have to popularize applications of mathematics. For example, in Kumaresan sir's book, when he introduced continuity, he talks about where continuity can be successfully employed. He comes up with a situation where there is a missile being launched, and he talks about the error, adjusting the error and adjusting delta and all, so that you will be successful in whatever purpose you want to do. Okay, although you talk about missiles and all, okay, just ignore that. But I'm saying that there are many places where you can actually give them real life applications. Try to do that as a mathematics teachers. For example, when you in functional analysis, when you teach all norms are equivalent in finite dimensional spaces, you say them this. For example, suppose I am doing something called supply chain management, or in data science or somewhere. I want to conclude the minimum distance traveled between cities or something, traveling salesman problem. Then you look at calculating the distance using what is this called, the one norm or the taxi cab metric. Sometimes it is also called as Manhattan metric. Okay, the other one is the Euclidean metric. So if I want to calculate the minimum distance, minimum of sum of the distances, if I use this Manhattan metric, the amount of computation you are going to do, the computer has to do, is much more smaller. It's order of n, whereas the other one is order of n square. Okay, these kind of things we have to say. For example, I can say many such applications in various places. Okay, but only thing is, for example, this abstract group theory. When you introduce a group theory, why do you need abstraction? You don't have to do. There is a recent thing, one of my friend, Dr. Sukumar, informed me about it few years back. Maybe it was in one of the MTTS program. And these are some advantages I learned from people associated with MTTS. People give me a lot of information. There is one person, his work is he does folding papers, origami. And then he discovers that by drawing lines, okay, on a piece of paper, like straight lines, continuous lines, and dotted lines. So he says continuous lines for mountain fold, dotted lines for valley fold. And he says certain axioms he puts in. If such axioms are satisfied by these lines, that piece of paper with that lines, if I fold accordingly, I can fold it into some structure. And he also says that with the help of mathematicians, given an object, you start with a goat, and if there is a goat, he converts into a stick figure and whatever important things that needed, and then from that stick figure he converts to yes kind of lines, like straight lines crisscrossing each other. Some are dotted lines, some are straight lines, and he says if it satisfies all this abstract structure, I can make a goat out of this paper from one single paper just by folding. And he shows he has done it, and he has done several things. So you have to search for, as a teacher, you should be curious enough to search for certain things. And when you teach basic courses, linear algebra, group theory, real analysis, everything, every concept you do, as much as possible, indicate them what are the possible applications. And now recent trend is, I always say these people, you learn some amount of Python, Java, good amount of linear algebra knowledge should be there. And then what else they should know is, they should know some amount of knowledge in supply chain management and optimization. The package is very good. They get 3 lakhs per annum if they are very good at all these things together. And especially in India, the supply chain management is a failure actually. But then in foreign countries, nowadays, due to this online marketing, and there are many warehouses which they need to consolidate and sort out various things like delivery, pickup, etc. Okay, all these needs undergo some optimization, and they need several people to come up with all these things. And if they are good up, you don't have to be extremely good, because extremely good people will do some of the tools needed for that, and they leave it as open source. You take it, and with some understanding what you have, you should know how to use it, open source packages, and then you'll be very successful. And that's what I learned recently. And that's all I want to say about interdisciplinary courses. Thank you all.
Priya, do I have time to say a few things?
Yes, ma'am.
Yeah. I mean, so see, I will come back to what I had said earlier, which is that most of the students who come to do an undergraduate degree in mathematics are not going to continue with mathematics. And I think it's extremely important for them to not only do their maths well, but also to have a sense of the society we live in. So I think it's extremely important to have a liberal undergraduate education. I have to say that I have changed my position on this. As an undergrad, I only wanted to do maths. I didn't want to do anything else. But as an an adult who's lived for many years after being an undergrad, I do realize that even if I do my maths well, even if I've become a good problem solver, I still need to have information about society in which I'm living in. And I think it's really important that students who come in to do an undergraduate degree in mathematics have the choice and the exposure to other disciplines. I think that's important. You can definitely see, too much of our syllabi making has been driven top down. So it's like, okay, this person has to do a PhD in mathematics. What should they do in masters? Okay, so they have to do so much in masters. In order to do that, how much should they be doing in undergraduate? They did up to so much in school, but there's this much they have to cover before they can do masters. So stuff the undergrad program. That's undergrad syllabi have got designed, and that's a terrible idea, given that not even 5% of your undergrad math students are going to continue with maths. Where would leave the rest of the students? See, so as I said, we had the opportunity to design things at our university, and I think you can do a good balance. Have 50% of your credits coming entirely from your discipline, put in all the foundational maths courses that you need. You can do algebra analysis, differential equations, numerical analysis, probability and statistics. Design in a way in which students know the application and see the applications. Have labs, teach them programming, and allow them to experiment in these courses and syllabi. The rest, you must have exposure to other disciplines, language, knowledge about the environment. Climate change is such an important issue. All of us are suffering through it in one way or the other. Why should our students be deprived of a situation where they don't know anything about it? You don't want to enter society being about things around you. So I think it's very important. Of course, the point is that the student who wants to continue with maths should also have the facility for doing much more or many more courses in maths. So make a choice. So have a 50% which is entirely coming from mathematics, and then allow the student the choice. Those who want to continue maths can probably use at least 25% or more of the credits can then come in mathematics, and by that mechanism you would have a situation where those who want to continue with maths, they've studied whatever maths they're doing in good depth, and then they can take off with that kind of understanding they have. Those who don't continue with maths have the freedom to explore other subjects. and other things which, find a path through it, because ultimately coming back to mathematics. So I think the point is that we have to rethink the way in which we design the syllabi for student, including, undergrad math students. I think, I don't know what it has a huge number of problems when it comes to implementation, and doing anything large scale is always very tough. Okay, but at the same time, I think it's important, and I think it has got recognized that we do have to equip our students to function in this world, and they cannot do that if their syllabus is entirely driven by what a student who wants to do a PhD in maths has to study at the undergrad level. And that's the worst thing to do. And we've been doing that for many years, unfortunately. And we have to change our mindset. And it's possible to do both these things, that is, give a good maths degree, which allows the student who wants to continue for the PhD to do as much as is required, but doesn't thrust it down every single math student's lives. That, I think, is important, and it's doable. That's my feeling from what we've done in our university. We all also keep learning and changing with our. Once we learn, that gives an input into what. I think with that, I will stop what I wanted to say.
Thank you so much, ma'am. So speaking about these interdisciplinary courses, there also comes the thought of building up a CV. And when you think of building up a CV, it requires you to do internships, especially in the industry area. And then also, even in academia, you have your friends who come and tell you, okay, I'm doing a reading project. Even in the undergrad level, I have had, personally speaking, I have had students from class 12 saying, okay, I'm doing a reading project or a research project for that matter. So how can a student, especially in the remote areas as well, now that they have a little bit of internet connectivity, get hold of such opportunities? What is the scope for such a student? Where can they get the information from? Also, when is it a right time for a student to take up such an opportunity? Because there are moments when you don't understand, okay, should I take up a research project? Should I take up an internship, or should I just focus on my course? Thank you.
You should name the other. All of us are wondering who has to start.
Sorry, ma'am, my internet connection was a bit poor. Okay, so Krishna, Geetha, ma'am, since I connected it to your question, can you please answer? Go ahead with it.
Yeah, sorry, internship. It's become also a trend now that students want to do internships. But again, don't do an internship unless you want to do it properly. If you just put things on CV, the most dangerous thing is if you put things on CV and you're not able to back it up. So if you put various internships, or even if you scored really well in your maths, okay, but you've done it only by cracking an exam and not really knowing the stuff, you'll get caught out in the interview. So first thing is that if you want to do an internship, you do it properly. Second is you have to decide what kind of internship. And I think there we go back to students at the undergraduate level are often trying to figure out what they want to do next. So I think in that sense, internships can be used to get a sense of the kind of industry or the kind of corporate structure, NGO world, where you think you might fit in, because often you're making a decision about your career without knowing exactly what you'd be doing within such organizations. And I think math students, again, any undergraduate students, there's lots of opportunity now that's available, whether wanting to go and work in media houses, whether it is journalism, whether you want to go into analytics, there's plenty of opportunities that is there. So, but the student has to, as I said, have a good balance between, sometimes what happens is you go do internships, they are of a much longer duration than your summer break. How do you handle your coursework as well as the internship then? These are all issues that come up. But it is a good idea for students to experience. I would suggest maybe not necessarily, whenever they get the opportunity, they can do that. But typically, the end of the first year before you start your second year, or even the end of your second year, is a good time to try and get some exposure, because these are all input having when you try to decide where you're going to work or what you're going to do next. I think it's the students who fall in love with maths and want to continue with maths, they've already decided their course in life. But a large number don't know. And so internship is also a good way of eliminating what kind of area you don't want to be working in. And so how do you find these things? I think it is definitely a problem if you're in a non-metro city. But I think, again, your teachers, and given that now there is so much available online, you can explore that. And I think MTTS kind of a thing, when you apply for things like this, or apply for summer programs, in a lot of science academies also have it. So academic internships, there's a whole plethora of things. Also, you can write to professors at various places and ask them if they're willing to apply over the summer. So there's, in terms of academic internships, there's plenty that's available. And because you'll get asked questions about it in the interview, and if you don't answer them well, then whatever chance you had of getting anything will go down. So that's one thing. The second is non-academic kind of internships that you can, again, campus placements, internship opportunities within your university and colleges, NGOs which are around working in your areas, they all are for students to work with them. So that's another thing. Now, one last thing I want to say is that often we often offer do workshops in our university for our students. In fact, Ajit came and did a workshop on Sage Math for our students because it was not part of the curriculum directly. And we've done LaTeX workshops, kinds of things that I saw in the MTTS program in this curry leaf offering that's happening. And I think these things, when they supplement a student having done their maths well, it really does help them. Because I do know students who have, I have a student who went into risk analysis after his undergrad degree in maths. And he was telling me that when he was facing several rounds of interviews, the fact that he had done these workshops, which we had organized for them, really did add to his, I mean, so the employer is trying to pick the best possible person for that job. And these things are add-ons which certainly help. They may not be, if you just do that, maybe it may not help. But if you've done your maths well, all these additional things that you do, they do count, because it tells the employer that here's somebody who's making really good use of their time and they've done it well. So I think these things do help them.
Thank you so much, ma'am. Krishna sir, I would ask you to briefly comment on this, and also, if possible, provide some opportunities that really an undergrad student can have for reading projects or internships. I know CMI has a summer research program for that matter.
Yeah, so so generally I agree with what Geetha said. See, this has become a trend to do these things. I think it is more of a fashionable thing. I think it has to come sort of out of interest and out of some particular use or interest in your subject, in a particular subject, and not just as a item you add on your CV. So and I actually think it's very important for students, especially in the beginning of their BSc, to just take a break for the summer and go home, read books, or just revise first year classes and generally relax, right? It's also important to refresh yourself instead of just going somewhere and not enjoying it. So having said that, see, the obvious ones that have been mentioned are summer programs organized by the academies. You have to apply and then they'll assign somebody. Various institutes have their own programs, and also you can always write to individual faculty members, but of course that may not work, because we sometimes get lots of emails and it's not clear how to judge who is serious, who is not serious. But I think it's helpful to talk to people in your college, maybe find out. I think nowadays it's easy to talk to people, contact people to find out information. You can write to some institute and students in that institute and ask them what options are there. They might respond more easily. So, and in CMI, actually, we don't have any formal program in maths for summer internship. Many of us have signed up with the academy's program, so they assign students, we take those students. Sometimes we also individually take students if they contact us. So I think these are the options that one has. And because unfortunately I think we don't have enough opportunities given the number of students that exist in our country. But yeah, so I think you will have to figure out the right institute and try to contact people and apply to all the established programs. Yeah, so that's all I think I can say for now.
Thank you, sir. So if any of other panelists have specific thoughts, they can share, because we are out of time a little bit.
So I just wanted, of course, I agree, just because having your impressive CV is not going to, just based on that, nobody is going to give a job, right? Ultimately, you are going to be tested it out. So instead of just looking at some internship at some place, I think what possibly I would suggest is that in the local, with the local faculty itself, if the student are doing some project, okay, that would really help. And that project could be even interdisciplinary, right? So, these days you can just search around. Mathematics is used everywhere. For example, just recently I gave some project to one of my students in water management. And that's a whole lot of mathematics is used there. So such things are available, and it could be even group project. So these are the things which will help rather than just, and see, even in the industry, finding internship is not easy. No industry will just like that accept student and let them work for a month or two. So whereas doing some project with their own professors, etc., will help. Yeah. Okay, so I just wanted to say, I mean, that will also help in to build some interdisciplinary skills for the students.
Tulsi, ma'am.
I don't think I have anything particular to add. I think most of the points have been covered by the other.
Okay, ma'am. Chandrashekaran.
Fine. Thank you.
Okay, so thank you. Now it's time for questions from audience. So if they have any particular question, they can raise hand. Okay, Ellen Charan. You are
on mute.
Yeah, I hope I'm audible now. Yeah. So I hear a lot of insightful thoughts today. My first simple question is to Tulsi, ma'am. The school education that you got until your class 9 was very interesting. Do such schools still exist, and what board is it, or what kind of pedagogical thing that you were under, where you are given resources and you are allowed to test yourself? That is very interesting. So I'm wondering, what kind of school were you?
The board was just ICSE, ISC, but this was one of these Krishnamurti Foundation schools. There are 5 or 6, I think, across the country. This one was in Bangalore, called Valley School. In Bangalore, I think there is a growing culture of these alternative schools, varying in quality. In different places, in other places, I'm not so aware. For example, I think Geetha can add, I believe I was talking to someone in Delhi recently, and I think that culture is not so much there. In Chennai, in Bangalore, I think this exists. I can tell you the flip side of this, which is such schools tend to be expensive. In my days, it was expensive. And since my time, it has got more expensive. I think when I was there, it was still more like a normal school. But these days, it's a sort of super elite school. I know there are people who try very hard to make such education accessible to everyone. But the numbers are extremely small. I would like to see more of this out there. But yeah. I think those with school-going kids will have a better idea about what the situation is like right now.
Thanks for the point.
Anyone else? Yes, Anthony.
Hi. My question is specific to what Krishna mentioned in the beginning. She mentioned that the exam system sometimes actually make us fall out of love with math because there is pressure to write the exam. But we are building it somehow. We can't ignore it. So is there a way we can find a balance so that we can learn and enjoy math and at the same time pass our exams decently? Thank you.
I don't have an answer to that. I think one of the points I think about a lot when I ask my students is, do you believe you are better at maths than you are at exams, or the other way around? I think I found in my life I was better at taking exams than I was at maths. And then there was always the pressure to study for the exam and put the learning off to later. There are many of my students whom I see are way better at maths than exams. And then their learning is not reflected in the exams. I'm not sure. Maybe the only thing I can think of, again, small scale, is to give students that confidence. If you feel you are good at something, you feel you enjoy something, perhaps that pressure of the exams are not there. But that's not something I think we can do as teachers alone. There's this huge ecosystem with parents, relatives, uncles, neighbors, all kinds of pressure coming on you to perform well in exams. As perhaps as teachers and students, we can try to appreciate someone's understanding or insights, even if the grades aren't high. I don't know. Maybe someone else has tried something else that works better. But I think we need to value different things in our students as well.
I think also exams need to be designed better. Somehow, and I maybe having just one exam which determines everything, you either fail or you have to really do well in it. That puts a lot of pressure on students. And so I think having some kind of a continuous assessment, if possible, different kinds of things, and designing whatever you do well in terms of getting students to think in the exam rather than just learn it. You know, Delhi University used to be full of the exams there used to have these terrible tricks. So if you knew the trick, then you would do well in the exam. I mean, that's not, to me, that isn't a measure of any kind of, you know, knowledge. It's just that you mugged up some trick and then you're able to do something. That's not a good idea. You shouldn't be having exams like that. So I think it's important to design an exam well. I really like the kind of system they had in Oxford where you had parts, okay, and it built up to something big. So you knew that the clues were hidden already in the earlier parts, but it was not very direct. It's not like if you solved the earlier parts, you automatically knew how to solve the main part. But the way it was structured, it sort of directed your thinking towards that somewhere you have to use what you have done in part A and part B to get to part C. And that I really enjoyed that, you know, because it was like a stepwise solving of a puzzle. It almost became like that. So I think you can design tests and exams nicely, but you know, doing an exam requires a lot more than just your fantastic understanding of mathematics. You also have to be able to, you know, perform within a time constraint and all of that. So it becomes a difficult.
I have a quick point to add. So based on about this assessment and things, recently MTTS Trust conducted a workshop where Professor Kumarasan has talked about different evaluating methods where we don't, where evaluation makes people think and also learn rather than just testing their understanding. I think MTTS Trust will also conduct such events, and that's one place where I found modern methods of doing assessment and collectively everything put together, including what Geetha mentioned. So I just wanted to mention that out here, put that out here.
I just want to add a point here, which is that I think some of us, I'm at a small private university. I think I have a lot of luxury there in that we are expected to use continuous assessment, and mostly instructors, at least the department, has complete freedom to design this. So many of our courses have a project component, group work, all of that is inbuilt. I think the point that Elan made is pretty important, but how to give teachers that autonomy is something perhaps beyond most of us. I know that in most colleges where my friends teach in Bangalore, there is a certain internal assessment component, but I don't believe the teacher has any chance to design that or even give their input in there. So maybe teacher autonomy is also one key to this.
It's a very important key to it. And Professor Kumarasan himself has mentioned certain tricks where in the traditional system, how to implement, start implementing their own ideas with minimal autonomy and eventually gain control over the assessment. Yeah.
I think Harini has raised her hand.
Good evening, everyone. This is not much of a question, but as an undergraduate student who's currently in her final year, and I lost 2 years, as you all said, to the pandemic, and I was very much interested in learning mathematics. That's why I took mathematics. But now, listening to all of you talk about what you all said, I have more faith, and it's reassuring to know that maybe I can learn more, and I have not lost much of my time, and there's more to learn. So thank you for this session. It was really good to hear you all.
Thank you, Harini. Now, anyone else have any questions from the audience? Okay, if not, we will thank our panelists. Okay, on behalf of Leaf, thank you very much. It was very nice interacting with you all and to hear your insights. So it was a great session. Like we came to know about your viewpoint, and pretty much we could also able to relate those pandemic things. And actually, I'm also feeling now relaxed after hearing these things. So as Harini said, now I'm feeling some faith in my mathematics career. Okay, so that's it. So can we take a group photo? Like if everyone is okay, you can turn your video on. So
yeah, we thank Karili for organizing this. Thanks a lot and giving us an opportunity.
Thank you. Thank
Yes,
you
yes.
again, others.
You're all doing great job.
Second, what Chandru said.
just Kiran? Okay.
Yeah, I'll take a screenshot in 1, 2, and 3. It's done. Thank you all.
Thank you.
Thank you.
Thank you.
Bye.
All the best.
Thank you.
Yeah.
Thank
Bye.
you.
Thank you all. Bye.
So we, the panelist team alone, will stay here. Let others leave. And
Shall I stop recording?
yeah, please. And also stop the live stream.